All right, thanks very much, AV team. Our hardworking AV team. They are underappreciated. All right, so welcome everybody, and thank you for coming to the second choreographic programming workshop held at PLDI. Very, very happy to have you all here. I just am going to say just a couple of brief sentences, and then I'm going to pass it on to my co-organizer, Dan, who's going to talk to you about some statistics. But I was just remembering, I think it was about 7 years ago, I first started really learning about choreographic programming and getting deep into it. And at that time, it was just this obscure little thing with a small but steady trickle of papers coming out of Europe, mostly. And in the last 7 years, it's blown up. And we're now are having a workshop at PLDI. There's people all over the world who are interested. It's a very exciting time to be involved in choreographies. And it's becoming a great community, and I'm really excited to be part of it for all of you. So thank you all for being part of that with us and for coming. I'm going to pass it on to Dan, who's going to actually tell us some stuff.
Yeah, can I go ahead and press this button over here? A few statistics. In case anybody is shy about being here and you're thinking, I'm not an expert in choreographic programming, what am I doing here? I tabulated the authors, and more than 70% of you guys it's your first time. You didn't attend 2 years ago, which is great. I think that's a great sign for our area. Thank you very much. Thank you for coming. And for the rest of you, thank you for coming back. That's also maybe equally important. And we actually have a pretty high, senior, I think, level of authors that only 15% are students. I don't even, who here is from Basis? I don't know. Are you industry? I don't know what to call you guys. Nonprofit research institute members. But most of us seem to probably have PhDs, which is a good sign that, like, okay, a lot of the experts are in here, and maybe an indication that we should get more students involved in this little bit of a scary area. But maybe this is typical for workshops. I'm not too sure. But interesting statistics. This is only the second one, so we'll see how things go along. I did also want to mention at the end, we're planning to go to Avanti Food Hall. It has all these different varieties of food options for you. We're just going to kind of free for all it. It's a 15-minute walk up to Pearl Street, which is a wonderful location, I'm told. And actually, I forgot to mention that before this, there's also going to be a business meeting for the CP workshop. It's going to be about an hour. I don't think we have even a concrete agenda planned, but just to figure out how to move forward with choreographic programming and so on. But aside from that, I hope you'll join us there. There's no sign up or anything like that. I'll remind you guys where everything is at the end with the closing remarks. But now I'll give it back to Andrew to introduce our keynote speaker.
Yeah, thank you very much. So without much further ado, I'm going to introduce Lindsay Cooper. So Lindsay Cooper is, I checked, she's still an assistant professor for like a couple more months at Santa Cruz. Her work on functional, concurrent, and distributed programming has been really, really influential over the years, including work on inventing LVARs, I believe, working a lot on the fundamentals of CRDTs, and more. And most recently, well, maybe not most recently, but one of the things she's been focusing on a lot recently is choreographies. So with her student, Gan, who I understand just graduated literally yesterday, she was one of the authors of Haskell, which does choreographies embedded in Haskell, and really invented the idea of choreographies as libraries. And so she's been thinking a lot about how we can build interpreters, especially interpreters for choreographic languages, everywhere inside of other languages and all sorts of things. So she's going to tell us a bit about that now. So thank you, Lindsay.
Audible on the stream. Thumbs up from the AV team. All right, thank you. Cool. Okay, thank you so much for that lovely introduction, Andrew, and thanks to everyone for being here. So I am going to talk about research, but I want to begin with a little bit of storytelling to set the stage. And the story that I want to tell, like so many stories, begins with this guy, Dan Friedman. So my story is that I was a PhD student at Indiana University from 2008 to 2014, 2015, if you count when I actually turned in the document. And when I arrived as a brand new PhD student in 2008, I took Dan Friedman's programming languages course, which was fondly known by people at IU as Intro to Dan. And in this course, you learn about what programming languages are made of by implementing interpreters. And that was how my PhD began, and that was how I got hooked on programming languages as a field. I didn't actually know for sure that I wanted to do PL when I started my PhD. I thought I might want to do databases. And my databases course was boring. Dan's course was interesting. So, and here we all are. So I was there at Indiana for 6 years doing this PL PhD, and that journey involved some twists and turns, which that would be enough for a whole other talk. But so long story short, I was eventually working with my advisor, Ryan Newton, on programming language abstractions for writing shared memory, deterministic concurrent programs. And we published some papers about this line of work using what we called monotonic data structures. And it was all about shared memory, or so I thought. So specifically not about distributed programming. But then, in the last year or so of my PhD, people who were interested in distributed computing, so specifically not shared memory, tracked me down and said, hey, your work seems to have a lot to do with our work. You should really read our work. So this is an example of that from Mark Shapiro back in 2013. He sent me an email. So he is, some of you might know, he's a well-known distributed systems researcher and one of the inventors of CRDTs, which Andrew mentioned in the intro. So conflict-free replicated data types is what CRDT stands for. And CRDTs are data structures that are used in distributed systems to ensure fault tolerance and high availability. So I got this email from Mark near the end of my PhD, essentially pointing out that I ought to be paying attention to his and his collaborators' work on CRDTs, and they were right, of course. So, of course, to make sense of CRDTs, I also had to do some other background reading on distributed systems. And when I started looking at the papers that these folks were recommending to me, it was kind of revelatory for me because up until then, I had really just been paying attention to PL research. And I didn't really look beyond PL research to consider the wide world of computer science beyond PL. But once I finally did look beyond PL, I realized that the field of distributed computing is fascinating and that I had a lot to learn from it. Distributed computing is full of beautiful and profound theoretical results, and it's also very practically relevant. And so that's when I began to really get interested in distributed systems. And of course, I haven't stopped being a PL person. PL is probably always going to be my research home. But these last 10 years or so, I have tried to study distributed systems from a PL person's point of view. And so this learning process was accelerated when I got a job at UC Santa Cruz in 2018, which, by the way, when Andrew said I would be there for a couple more months, that doesn't mean I'm leaving. It means my tenure case is working its way through the
Assistant for a couple
process. Yes. But anyway. When I got this job there in 2018, I was suddenly expected to teach distributed systems. So that meant I really couldn't fake it anymore. I had to really deeply understand something about distributed systems instead of being a dilettante like I had been before. And that influenced what research problems that I was interested in. So these last several years, where my mind has been research-wise has been in the world of distributed systems. And my students and I have been going around sneaking distributed systems ideas into PL conferences. So these papers listed here are just a few examples from the last 6 years, a couple of which I'll say more about later. But finally, after years of this, about a year and a half ago, I had another realization. And this is one that is not going to come as a surprise to Dan Friedman or any of the people who are part of Dan Friedman's intellectual tradition. And I like to call those people the Dan Aspera. And that realization was that it was actually about interpreters the whole time. And so having been on this long side quest into distributed computing all these years, even so, a lot of what my students and I had been doing was still all about interpreters and interpretation. You know, what can I say except oops? So in the rest of this talk, I want to discuss a couple of our group's projects that exemplify this realization that I had. Both of these projects are about distributed systems, but I'm going to talk about them through the lens of interpreters. Okay, so this, of course, obligates us to try to answer the question of what is an interpreter? And so fair warning, I'm going to ask you, the audience, what you think an interpreter is in a second. So start thinking about your answer. Okay, so while you're thinking about that, let's see what the dictionary says. This was sent to me by my friend Ken Sean. Someone or something that interprets. Okay. All right. Well, that's a true but unhelpful answer. There was also another dictionary definition, though, that's computing specific. So let's see what that one says. A machine that prints on punch cards the symbols recorded in them by perforations. And a computer program that executes each of a set of high-level instructions before going to the next instruction. Well, okay, you tried. I think this definition is bad also. I think we can do better. Does anyone here have an idea of a better definition? Any suggestions?
I like 2B.
2B? Okay, 2B is not too bad. I mean, I think it's better than the others. Other suggestions? Sure.
A program that runs non-native instructions.
A program that runs non-native instructions. Okay, okay. All right, I think these are better than what is on the slide. Okay, so for the purposes of this talk, I'm going to say that an interpreter is something that takes syntax and produces semantics. And I really like the generality of this definition. So it lets us plug in notions of syntax and semantics for the domain that we're interested in, whatever that domain may be. And the domain doesn't even have to be computing specific. So, for example, and this analogy is due to my friend CF, we can think of a choir as an interpreter. I happen to be a choral singer, so this analogy really clicks for me. So it's the choir's job to interpret a musical score and ultimately produce audible music, perhaps aided by a choir director, which for this purpose we can think of as being part of the choir. And in computing, we might think of an interpreter as something that takes a program and produces some kind of value. I'm not even going to attempt to nail down a definition of program or value. But I will point out that the value you produce might even itself be a program, in which case, what is this last arrow on this slide here that's labeled with a lambda? It's a compiler. Yeah, you got it in one. So at the risk of really annoying people who might be here at the Conference on Programming Language Design and Implementation, I'm going to argue that for the purposes of this talk, a compiler is a special case of an interpreter. And I would also argue that every programming language is an interpreted language, because sooner or later your code's going to be executed by a CPU. The CPU is an interpreter, so it's interpreters all the way down. But there's another key thing beyond this that I want to mention about what interpreter means. So if you'll continue to indulge me with this choir analogy. So a musical score for a choir will typically have different parts that different people sing. And if we say that syntax is interpretable, that usually connotes something about the structure that that syntax has. In particular, it says something about how the interpretation of a given input is determined by the interpretations of its subcomponents. And then the result you get is compositional. To be able to do this, there has to be an obvious way to break down the input into its subcomponents and then put it back together. In other words, it has to be inductively structured data, like an abstract syntax tree. So what I want to do next is dig into a couple of specific places where this notion of interpretation has showed up in my own work over these last several years. And I'm going to focus on 2 lines of work from that list that I gave earlier: library level choreographic programming and causal separation diagrams. So as pointed out earlier, a lot of people here may be new to choreographies, or at least new to the CP workshop. So I'm going to talk about choreographies. I'm going to discuss the basics. And I won't be getting into all the technical details, but if you're interested, I'm happy to dig into the details in Q&A or to chat with folks later. Okay, so let's jump in. So let's talk distributed systems. So in the world of distributed computing, we're usually often concerned with message passing, right? And the idea is that you have some independent nodes that communicate with each other via some kind of network by sending some kind of messages. And they don't share memory, so the only way for them to coordinate with each other is by passing messages. And as a simple example here, let's suppose that our independent nodes are Alice and Carol. So typically there's some kind of desired global behavior of the entire system that we want. And it could be something like Alice and Carol establish a TCP connection with each other. Or it might be something higher level, like Alice and Carol coordinate to take a snapshot of the execution, or Alice and Carol coordinate to reach consensus on a value or on a sequence of values. Either way, nodes have to somehow collectively accomplish something global, somehow accomplish this global behavior, but they have to do it by only taking local actions. So each node can send messages, it can receive messages, and it can take internal actions, and that's it. So if we want to do, for example, this incredibly simple protocol in which Alice sends a message to Carol and Carol responds, how do we program it? Well, we can assume for now the existence of send and receive functions that actually implement the message transport somehow, be it with TCP or via pigeon post. And let us not worry about the details of how that transport layer is implemented. And let's just assume that the transport layer exists, and now think about what Alice and Carol have to do, assuming that it exists. So each of Alice and Carol might run a node local program. And for Alice, it might look like this. Alice might send a request to Carol, and then wait for a response and store the response in this variable y. Meanwhile, Carol would run her own node local program, which might look like waiting to receive a request from Alice, storing that in a variable, doing something to handle it, and then getting a response and sending the response back. So this is just about the simplest distributed program that I could think of. But even here, notice that Alice and Carol are just utterly dependent on each other to faithfully follow the protocol. So for instance, suppose that Carol neglects to call that first receive. Well, even though Carol messed up, now it's Alice's problem. So Alice will now wait forever to get a response for her message hi, or maybe she'll time out and report an error, depending on how send is implemented. And in general, nodes have to exchange messages in this carefully executed dance, where every message that's sent from a node ought to be expected by some recipient, and vice versa. And if one node is running buggy code, things could go wrong for someone else. And of course, if we add more nodes to the mix, then it only gets more complicated. So let's say that Alice is sending Carol a request, and then Carol is supposed to pass the request along to Bob and get some sort of an acknowledgement from Bob, and then finally respond to Alice, acknowledging her request. So in this scenario, Alice may or may not know that Bob exists, right? But nevertheless, if Bob is misprogrammed, that could spell disaster for Alice. And this example calls to mind this classic quote from Leslie Lamport, in which he defines a distributed system as a system in which the failure of a computer that you didn't even know existed can render your own computer unusable. So the challenge then for programmers is to reason about the implicit global behavior, like Alice, Carol, and Bob together accomplish a task, while writing these explicit local programs that call send and receive that actually run on each node. So this brings us to the idea of choreographic programming, where the idea is, let's just make that global behavior explicit. So in choreographic programming, we don't write the local programs at all. Instead, we write a single global program that's called a choreography, and then we generate a collection of local programs, one for every node, via endpoint projection. So looking at this choreography here, every choreographic language has some kind of operator like this squiggle arrow on the first line, which is usually pronounced com because it's denoting communication between these two parties. And a com is expressing both a send and receive at once. So when this choreographic program is projected, every occurrence of Alice on the left-hand side of a com is going to turn into a send for Alice. Every occurrence of Alice on the right-hand side of a com is going to turn into a receive for Alice, and likewise for other nodes. And thanks to this mechanism, as long as our endpoint projection is correct, we can rule out the possibility of mismatched sends and receives, and therefore rule out a certain class of bugs in our collection of choreographic programs, or sorry, in our collection of local programs. And so in a nutshell, that's the benefit of choreographic programming. So at this point, I want to acknowledge one of the elephants in the room, which is that with what we've seen so far, choreographies per se don't do anything to help should one of these nodes crash, or should one of these messages be lost. And those fault tolerance problems are present here just as they were in the non-choreographic version of the code. So choreographic programming by itself doesn't do anything to address that particular challenge of distributed programming. What it does do is specifically gives us a way to rule out a class of programming errors that stem from a programmer not calling send where they should, or not calling receive where they should, to match up with another occurrence of send or receive. So in a simple program like this with only two parties, that might not seem like such a big deal. But once more parties are involved, it's not that simple. And it's in that setting where choreographies really shine. So let's look at an example with three parties and with some more interesting control flow. So here, this is a slightly more interesting protocol. Let's say that Alice wants to interact with Bob, but Bob stops her to check her credentials first. And so, by the way, this example is straight from the choreographic programming zine that my student Ali and I published about 1.5 years ago, which you can find on my website if you want. And in the zine, it's that Alice wants to go to Bob's birthday party, but she's stopped by the bouncer Bob. Okay, so in this protocol, Alice's credentials have to be verified through Bob before she can interact with Carol. Bob will run a check function on Alice's communicated data, and depending on the outcome, Alice will either get an access token from Carol, that's the success case here, or otherwise not. So this diagram represents two different ways that an execution could go. These are both different possibilities in this execution. So to express this in a choreography, we can have conditionals at the choreography level. And here's what that looks like. So on the first line here, there's our squiggle arrow again. This notation, alice.credentials.com bob.auth request, says Alice is going to compute her credentials, send them to Bob, who will receive them and then store them in this variable called auth request. And then we have this conditional. So the conditional check takes place locally on Bob. Then depending on what branch we take, Bob will communicate success or failure to Carol. And Carol will either communicate the token to Alice or tell Alice that she can't have it. What I think is useful to point out about this execution is that even though the execution is spread across three different parties here, if we think about it globally, this is actually a sequential program in which steps happen one after the other. And we can even see from reading the choreography that the choreography really looks like straight line code. In fact, our choreography looks remarkably similar to our informal diagram. If we were to write this code as a traditional distributed program where there are three different programs running on three different participants, then the control flow would not be as obvious. So to actually run this, we need to endpoint project. Endpoint projection will take this choreography and turn it into versions that will run on Alice and Bob and Carol, respectively. And this can be done automatically by the choreographic language implementation. And this is pseudocode, right? I've written some pseudocode to give an idea of what the projected code might look like. But notice that, like I said, in the projected code, the control flow is not quite as clear. You might have to stare at it for a while to figure out, okay, what's supposed to happen first, what's supposed to happen second, and so on. So another thing that choreographies could give us is readability. There's a side note here about knowledge of choice, but I won't go into that. So we didn't invent any of this stuff. Choreographies have been around for a long time. So here's an abbreviated timeline of choreographic programming. I'm starting a bit later than Fabrizio started when he gave a version of this timeline at his choreographic programming keynote talk 2 years ago. His started in the 70s. But I'm going to pretend that time began in the early 2000s. When the W3C Web Services Choreography Working Group, alongside a group of invited experts from academia, developed a draft specification for a choreographic language. And it was called Web Services Choreography Description Language, or WSCDL for short. Catchy name. However, this WSCDL language was not meant to be executable. It was only a specification language. Fast forward to 2013, when Marco Carbone and Fabrizio Montesi published their work on the core programming language. So core pioneered the idea of a executable choreographic programming language that used endpoint projection to compile choreographies to runnable node local programs. And then, not too long after that, Fabrizio teamed up with Saverio Giallorenzo and Marco Peresotti to create the Coral programming language, which was intended to be useful for realistic programming. So Coral is designed to be familiar to Java programmers, and the creators of it made a point of using mainstream object-oriented programming abstractions. And the Coral compiler compiles choreographies to executable Java code. And then in 2022, Andrew and Deepak Garg created Pirouette, which combined choreographic programming with higher order functional programming. So this paper was my first exposure to choreographies. It made a splash in the functional programming research community, which I'm part of. It won a Distinguished Paper Award at Popple that year, and it's how my students and I found out about choreographic programming for the first time. It is also notable for its mechanized proof of deadlock freedom. So my student, Gan Shen, wanted to try choreographic programming after reading the Pirouette paper, and he wanted to try implementing a choreographic language himself. Being who he is, the approach that seemed most obvious to him was to do it as an embedded DSL in Haskell. And the idea is simple, and what's funny about this was that my student Gan wasn't trying to do something novel. He just wanted to learn about choreographies. But it turned out, to our surprise, that this idea of implementing a choreographic programming language purely as a library hadn't been done before. And so this appeared at ICFP 23, where it also won a Distinguished Paper Award. So for a couple of years in there, every paper about choreographic programming at PAC-MPL was winning a Distinguished Paper Award. Sadly, no longer the case. Okay, so let's dig in a little bit to how Haskell works. So I'm going to contrast this with the traditional approach to choreographic programming, which is exemplified by Coral here. In the traditional approach, you write a choreography in a standalone language, and then you compile it to executable code to run on all of your endpoints using a standalone compiler. And this works fine, but it does mean that you need this purpose-built compiler and this purpose-designed language. In Haskell, on the other hand, choreographies are expressed as programs in an existing host language, in this case Haskell, and the choreographic language constructs and endpoint projection are implemented by a host language library with no additional compiler support, no additional runtime support beyond what that host language can already do. So in particular, this choreographic language, Haskell, is implemented in Haskell as a monadic DSL using something called a freer monad, which separates the interface and the implementation of effectful computations. And by itself, the language doesn't assign any meaning to the choreographic operators like that squiggle arrow. It just accumulates them as a big term. And then we dynamically interpret that term based on the location where the code is being run. So for instance, in Haskell, the COM operator is going to be dynamically interpreted as send if you're the sender, and it'll be dynamically interpreted as receive if you're the receiver. And if you're anyone else, it's a no-op. So this idea of a DSL embedded in Haskell using this monadic approach also is not new. This has been done for a long time, pioneered by people like Paul Hudak. And they've written at length about the benefits of this approach. And the usual benefits of this approach apply here. So because Haskell choreographies are really just Haskell programs, it means that a Haskell programmer can take advantage of the Haskell ecosystem. So Haskell can be installed just like any Haskell library. It can be compiled like any Haskell program. And best of all, it can use that formidable ecosystem for development, debugging. So if you have any tools that you like to use, it can use those tools. If you had to use a standalone language, that ecosystem wouldn't be there for you. You might not even have syntax highlighting unless the developers chose to implement it. Whereas with this embedded DSL approach, we get that stuff for free. There's another plus side, I think, to this embedded DSL approach, which is that it makes it easier to integrate choreographies into bigger non-choreographic systems. So there's no need to change languages just so that you can implement some part of the system choreographically. I think this is an important point because choreographic programming honestly might be a great fit for certain parts of a system and not for others. You might have a system where almost all the computation is local, but then you have some small, occasional, short-lived network interaction, maybe to do authentication or something. So that's an argument in favor, I think, of the library level approach to choreographic programming. So one of the consequences of this library level approach is that endpoint projection actually happens at runtime. So endpoint projection is just a regular old function. So let's take a look at the type of the endpoint projection function in Haskell. And I hope to convince you that it's really just an interpreter. And I promise you this is the only line of code that I'll make you look at in this whole talk. In fact, it's not even a line of code, it's just a type signature. So endpoint projection takes two arguments. The first argument is this choreo thing here, which is a choreography. So endpoint projection takes one of these choreographies. The second thing that it takes is a location, which is the place we want to project it to, like Alice or Bob or Carol. And endpoint projection returns something called a network, which you can think of as a low-level program in terms of sends and receives. It's been specialized to the particular location that you gave as an argument. So for the Haskell enthusiasts here, both choreo and network are freer monads. But we can think of things of type choreo and things of type network as just being programs. And the choreographic operators that are in choreo programs are things that you can use when writing choreographies. And these all get interpreted to things like send and receive in network programs. So choreo gives us a syntax for choreographies. And on the network side, I put semantics in quotes here because this isn't actually semantics, it's still just syntax. And then that will get dynamically interpreted to the actual meaning of send and receive and so forth. So the actual meaning of send and receive and so forth is going to be supplied by a network backend. And Haskell has a couple of those that you can plug in and choose between. So there's an HTTP backend that you can use for HTTP network transport. There's a local backend that implements these send and receive functions as communication among threads on a single machine. So that's endpoint projection. It's just an interpreter. And then for development and debugging purposes, we also have yet another different interpreter that can just interpret these choreo computations directly as single node programs. And that's a nice thing about the choreographic approach, I think, is that you can, if you want, directly interpret a choreography for debugging purposes as a local program instead of projecting it. So you don't actually need a distributed system to smoke test your code. You can observe the behavior of it in some sense locally without actually having to have a network for it to run on. Okay, so returning to our timeline, it is really exciting how after Haskell came out in 2023, a bunch more choreographic languages as libraries have popped up. And so some of them are from our group. So multi-core is a successor to Haskell, developed by Mako Bates, who is here. Chorus is our choreographic programming library for Rust, and ChoreoTS is our choreographic programming library for TypeScript. But what's even more exciting to me is that a bunch of these are not from our group, and both academics and non-academics are working on this. So there's Core Camel for OCaml, which was from one of Anil Madhavapeti's students, which appeared at the OCaml workshop. There's Corex for Elixir, which is from Ben Greenman's group at Utah, and his student Ashton Wiersdorf. There's Coret for Racket, which is from Andrew and his group at Buffalo. There's Unicorn, which is a choreographic programming library for a distributed programming language called Unison. And the most recent one I've heard of is called Mooncore, which is for a distributed programming language called Moonbit. All of these are libraries, just like Haskell. But they all do it a little differently because they're all using the idioms that make the most sense in their respective languages. So, for instance, Coret is built on top of Racket. And racketeers here will be unsurprised to hear that it's done using macros. Likewise, Corex uses Elixir's powerful macro system. And Unicorn uses a language feature in Unison called abilities, which is better known as algebraic effects to PL folks. So I love that library-level choreographic programming is spreading and that people are doing it in ways that we had not thought to do, which is really cool. I also want to acknowledge all the students who worked on this stuff. So the Haskell library was created by my student Gan Shen, more about him in a second. Chorus is partly the work of my former master's student Shun Kashiwa, who is also the second author on the Haskell paper. And that work was also a collaboration with Mako, who did his PhD with Joe Neer at Vermont, and he's also here today. And then, of course, these other projects also had student leaders. So lots of great student work here. Speaking of Gan, though, I just want to take the opportunity to mention that Gan just defended his dissertation entitled Library Level Choreographic Programming 1 week ago today. The photo on the left here is Gan and me in the lab after his defense talk, holding the gifts that we gave each other. And the photo on the right is Gan at the commencement ceremony yesterday in Santa Cruz with his proud parents who came from China to celebrate with him. And this is a proud moment for me too. Gan's my first PhD graduate. He's not here at the CP workshop because he's now taking a well-deserved vacation with his parents and showing them the sites. But he is really the reason I'm part of the choreographic programming community. So I want to take a moment to celebrate his accomplishments. So, yes, thank you. So that's it for the first line of work that I wanted to talk about on library level choreographic programming. And next I want to turn to this other slightly different line of work. This is not about choreography specifically, but I hope that some of you will recognize something choreographic in it a little bit. This is causal separation diagrams. So let's talk diagrams. So people who work on concurrent and distributed computing have been using diagrams like this since at least the 1970s in an effort to wrap our heads around how concurrent and distributed systems work. I've been using them throughout the talk, and you might have drawn one yourself on a whiteboard recently. I call these things Lamport diagrams. I got that terminology from my colleague Peter Alvaro, who got it from Joe Hellerstein. Sometimes people also call them sequence diagrams or time diagrams. They go by a wide range of names. So these diagrams visually depict the events of interest in a system, often things like when and where a message is sent or received, and the causal relationships between these events across time and space. And the way that these diagrams let us visualize causality is so useful that we see diagrams like this all over the place at all levels of industry and academia. But they are just pictures, and they can be hard to manipulate. As my student Jonathan says, in the worst case, you can barely manipulate them with a whiteboard eraser, much less with math. But they could be formal objects. So let's think about how to formalize these things. So to reason formally about executions, we need a formal model of executions. Lamport's own 1978 model goes more or less like this. So first we have a collection of processes that models a set of locations in the system. And then every process has a sequence consisting of the events that occurred on it. And events can either be message sends, or they can be message received, or they can be internal events. And then finally, we identify the pairs of events that comprise messages, where information is being propagated from one location to another. So for example here, A1 is an internal event on process P1, but A2 happens to be a message send, and its corresponding receive event is A5 over on process P2. So what you see here on the right is a completely standard way to capture the information that's in this picture. It gets used all the time, but it does have some potential pitfalls. One issue with this representation is that it does not stop you from representing something that's physically impossible, like a causal loop. So here's an execution that couldn't actually happen in a distributed system. So here we have P1 is sending a message to P2, then a little time goes by, and then P2 sends a message to P1, which arrives before the original one was sent. So this couldn't happen because time goes in one direction. So, but this representation that we have here didn't stop us from representing that execution. So if you want to avoid something like this, you would need to check or assume that your data is self-consistent, and the structure of the data itself doesn't help you avoid this situation. That would have to be checked separately. This representation also doesn't stop you from representing inconsistent cuts. So here's what I mean by that. A consistent cut in an execution like this is something like this blue line with a happy face. So a cut is something that separates the events of an execution into a clear past and future. Here the past is above the line and the future is below it. So if an event is on the past side of the cut, then everything that's causally before it should also be on the past side of the cut for this to be what we call a consistent cut. So this blue one here is in fact a consistent cut, kind of trivially because the two events that are there don't have any preceding events. So there are no events that are causally before those two events. An inconsistent cut is like this one represented by the red line with the sad face here. So this one fails to have that property. So here, A5 is an event that's on the past side of the cut, but A5 is the reception of this message that was sent over here by process 1 at A2. So A2 causally precedes A5, according to Lamport's happens before relation, but A2 is on the future side of this cut. So the traditional model does not help us avoid inconsistent cuts. If we tried to just model cuts or inconsistent cuts by just taking a prefix of these sequences, P1, P2, P3, it might sometimes turn out to be a consistent cut, and it might not sometimes. So that's not going to be good enough. And the problem is that there's not a connection between the processes that we're splitting into past and future here and the messages that we need to respect. You might have heard of the software development dictum, make illegal states unrepresentable, which I think is due to Ron Minsky. And as my student Jonathan Costello puts it, this representation of executions makes illegal states all too representable. So what should we do instead? So to understand what's problematic about this traditional approach to representing executions, let's take a closer look at it. So here's the same execution we were looking at before, but I've now turned the diagram on its side, I've turned it 90 degrees, and I've taken away the labels on the events. But it's still the same execution. It's got the same structure as before. The only difference is that now I've added some dotted and dashed lines, which help make the structure of the execution more explicit in the diagram. So let's talk about what those dotted and dashed lines are showing us. So in this traditional approach, the top level structure is to split things up into processes. So the first thing we're going to do is visually separate the processes from each other with these dotted gray lines. And those indicate spatial boundaries between the processes. And next, each of the individual processes has a sequence of events in time. And we can make that explicit too by putting these temporal dashed lines in between events on each process. Unfortunately, we can't really do the same thing with messages. And that's almost by design. We decided to make the order of events within a process our top priority. and messages are a different kind of entity. But notice how these messages always cross these gray dotted spatial boundaries, which run horizontally, instead of crossing these blue temporal boundaries, which run vertically. So the process local edges that cross over these blue boundaries, those are inherently being causally ordered or temporally ordered by the structure of the data, but these ones are not. So the fact that messages are leaking across these spatial boundaries this way is actually what makes it impossible, or makes it possible, to accidentally construct an inconsistent cut, like I was showing before. And this happens because we decided to prioritize the spatial boundaries between processes instead of prioritizing the temporal boundaries between events. So what happens if we change it up? What happens if we try to lay down these blue dashed lines first? And that's exactly what our approach does. So here's that same execution, but now represented using one of our diagrams, which we call causal separation diagrams. So here, the first thing we've done is lay down enough of these vertical dashed blue lines to separate every event. That's what these vertical lines are. So instead of splitting up by processes first, we're splitting it up by global time steps, where by time I mean logical time, of course. And next, within each of those global time steps, then we can add the dotted gray spatial boundaries between each distinct location. And we end up with a different sort of way of decomposing this execution into pieces. So the original way of decomposing it first decomposed into processes and then split those up. This decomposition suggests a single sequence of global steps. And then these global steps are composed of local steps for every location in the system. So here, for example, we've got 4 global steps arranged from left to right. And they're separated by these blue dashed lines. And then each global step happens to contain 3 local steps that are separated by these gray dotted lines. So this choice to prioritize the temporal boundaries over the spatial boundaries is the fundamental idea of CSDs. I've been saying temporal boundaries here, but I could just as well call them causal boundaries as well, because potential causality follows the flow of time. So that's where we get the name causal separation diagrams. Something else that might jump out at you is that some of these local steps don't actually contain an event at all, right? So like this one here, for instance, there's no event. So that's because our processes observe different numbers of events, and separating out all the events on one process is going to cause the events of another to appear more spread out. And so this decomposition also isn't unique. It depends on where we chose to lay down those temporal boundaries. So we know that for any distributed execution, there's going to be a lattice of consistent cuts. That's well documented in the literature. And we're only picking out a particular totally ordered sequence of consistent cuts from that lattice. In fact, each of these blue dashed lines is a consistent cut through this execution. But here's what's most interesting. Both messages and processes are now evolving across temporal boundaries. So you see now how the messages are crossing over these blue dashed lines, as well as events that are happening in sequence on a process. So information never propagates directly over a spatial boundary. And as a consequence, a diagram that can be decomposed this way necessarily won't have any of those causal loops that I talked about before. If it did, we wouldn't have been able to cut that loop with a consistent cut. So in other words, if you can construct a diagram this way, then the execution will be causal by construction. So here are all of the different kinds of local steps that we can build up these diagrams from. The first 2 should look familiar. A tick is just a local event on a process. A no-op is the absence of an event. The last 2, a swap and a sock, don't model any actual events. Instead, they just allow us to kind of rearrange the wires through the diagram so that processes can communicate with more than just their immediate neighbors. And you can think of these 2 tiles as being, or these 2 building blocks as being somewhat akin to the structural rules in a logic. And then the middle 2, fork and join, Those model the two halves of a traditional message. However, unlike a traditional message where we saw both the process and message state kind of going in different directions, where the process state continues along and the message state kind of goes out the side, instead we see them kind of both coming out the right-hand side here, or coming in the left-hand side. And that's on purpose. Our model actually doesn't distinguish process state from message state at all. So we're referring to the inputs and outputs of this tile here, fork or join, uniformly as one thing. We call them sites. So a site is just a place where state can exist. So we don't have a separate notion of process and message. We just have this one thing, sites. This was my student Jonathan Costello's innovation, and it honestly took me a long time to get my head around. I'm so used to thinking of processes and messages as the fundamental building blocks. And treating them as the same thing seemed weird to me. But it actually makes sense to me now. They're both places where state can exist. So a process sending a message to somebody else is just a site forking off a piece of its state out into the world as a new site. And a process receiving a message is just two sites joining together. So now you can stick these tiles together and get a consistent causal separation diagram. I left it out of this slide for brevity, but every one of these tiles also has a type, which says how it's allowed to be composed with other tiles. And so for the fancy type enthusiasts out there, these are in fact dependent types. And I haven't shown it here, but we also have commutators for composing these local steps into global steps, and then for chaining global steps together into a full execution. And the type of every tile will tell you how it can be composed with other tiles or not, vertically or horizontally. Okay, so what does all this have to do with interpreters, which are the topic of this talk? So earlier, when I was talking about what interpretation meant, I said that if we say that if a syntax is interpretable, that usually means that the interpretation of an input is determined by the interpretations of its subcomponents. And to do this, we have to have an obvious way to take the input, break it down into subcomponents, interpret them, and then put those interpretations back together. That obvious way to break things down and put them back together is what we call an induction principle. And for the traditional formalization of executions that I showed first, we unfortunately don't have one of those nice induction principles. We just have a set of processes and we have a set of messages, and the structure of the data didn't give us any guidance on how we were supposed to break things down and put them back together. So executions that are represented in the traditional way are not particularly amenable to interpretation, particularly not if you want to use a mechanized proof assistant that encourages inductive definitions of data structures. But if you have an execution that's represented as a CSD, it comes with this lovely structural induction principle, since it's just a list of global steps. So to take a CSD apart, you can just peel off one global step at a time. To put it back together, you can just glue on one global step at a time. And that inductive structure is what makes CSDs amenable to interpretation. So CSDs give us a formal, inductively defined syntax for representing concurrent executions. And it's something that you can actually write interpreters for. And that's exactly what we do. So in our paper, which we published at UPSLA in 2024, we discuss a few different ways of interpreting these things. So that is 3 different ways of giving this syntax as semantics. The most obvious one is interpreting CSDs into what we call causal paths. Causal paths are a proof-relevant analog of Lamport's happens before relations. So instead of just saying that 2 events in an execution are causally related and just asserting that, CSDs actually let you accompany that assertion with evidence of the causal relationship between the events. And that evidence is just a path through these diagrams. The second way to interpret these things are into logical clock functions, which assign to every event in these executions some sort of logical clock timestamp. And this interpretation lets you, this interpretation is parameterized over a particular logical clock implementation. Like vector clocks or Lamport clocks or matrix clocks. So you can instantiate the same machinery over different logical clocks. We did that for a bunch of clocks. Logical clocks like these are widely used in distributed systems to represent causal relationships. And then the third way that we give to interpret CSDs is into proofs that clocks respect causal paths. So the reason why people use clocks, logical clocks like this, is because they want causal information. Because thinking about data that's kind of spread out across the whole execution, like these causal paths, is more complicated than reasoning about just numbers at different events. So we want to be able to reason about logical clocks and then have that reasoning be sound and have that actually correspond to a logical, or to the causal relationships between events. And a logical clock that respects causal paths is one that satisfies Laporte's clock condition, which is the thing that makes a logical clock a logical clock. So using CSDs, we can give a proof of that clock condition that's parametric in the choice of clock. So this is not news to anyone who, to hear that these clocks actually do respect the clock condition. Of course they do. If they didn't, then they wouldn't be useful. But a lot of verification efforts kind of just take this on faith, including my own previous work. So there'll just be an axiom somewhere that says that clocks preserve happens before relationships. Or they won't even have an axiom. They'll just use logical clocks, and then they'll say, look, as you can see from the happens before relationship, So, or if there is a proof, it'll be like an ad hoc proof that's specific to some particular logical clock implementation. Whereas this proof is generic, and it applies to this whole class of clocks. So this interpretation-based approach to verification, doing verification by writing interpreters like this would be really awkward and difficult if we didn't have this inductive data structure to work with. But with causal separation diagrams, it kind of just falls out naturally, which is cool. So we're at the end. To sum up, I talked about 2 different lines of work from my research group that turned out to be about interpreters all along. So I talked about library-level choreographic programming, which lets programmers write distributed programs as these single unified programs in their favorite language, and then dynamically project them to multiple endpoints. And I talked about causal separation diagrams, which are inductively defined data structures that are designed for elegant mechanized reasoning about causal relationships in concurrent executions. But really, I could sum up these 2 lines of work by saying this line of work about library-level choreographic programming is just asking the question, what if endpoint projection was an interpreter? And the work on causal separation diagrams could be summed up as asking, what if you could write interpreters for Lamport diagrams? So the takeaway I have for you is you can't go wrong by studying how interpreters and interpretation work, and then go study something else and apply your knowledge to that new domain and reap the rewards. And that's all I've got. Thank you.
We have plenty of time for questions. Let me grab your mic so that I can give it to you if you have questions. Dan, can you keep an eye on the Discord and see if anybody has questions there?
Sure. Wait, what Discord?
The PLDI Discord?
No, not the Discord. Okay.
Is it the PLDI?
Yeah, this is the PLDI Discord.
Hi.
Thanks for the talk.
Well, make sure it's not.
Hello?
The room mic might be off, or the room speaker might be off, but
Okay. Thanks for the talk, Lindsay. So when you first said cut,
yes.
and then when you also showed the tiles,
Uh-huh.
and you said that the last 2 were kind of like logical axioms and you think, do you think there's potentially a 4th interpretation into some sort of logic? Linear logic? This is my own bias.
Okay,
That's
yeah.
I have to talk.
Yeah, that's an awesome question. Thank you so much. Well, for sure, this is not all the ways to interpret CSDs. In fact, the whole point is that they're interpretable, choose your own interpretation. Something that we spent a little while thinking about was, couldn't you have a program logic based on CSDs? We didn't end up really pursuing that yet. But it's a great question. And one thing to point out here, though, is that a single CSD like this just represents one execution. It doesn't represent a program. So if we wanted to represent programs, right, with CSDs, then we might need to extend CSDs, right? And we have thought about that a little. What if CSDs had conditionals, right? what if CSDs were more like choreographies? I think there's something to do there. My student Jonathan, who led this project, has moved on to something that's overlapping but different. So they're no longer focusing all their effort on CSDs, but I think it's a great question, and I would love for somebody to take that idea and run with it. So yeah, maybe we can talk about it more later, and I could even connect you to Jonathan if you were interested. Cool, thank you so much.
So in your early example on projections, you were showing a conditional, and this conditional looked like it could be easily misprojected because what if an actor doesn't receive in both branches? How do you address this?
Right, terrific question. So I think I very briefly mentioned as I was on this slide that there was something to say about knowledge of choice, but that I wasn't going to say it. So I've saved it for the Q&A. So this is a great call out. So one thing to think about when you're thinking about how to do endpoint projection is the question of how are processes going to know what branch to take. So here, when we're projecting this program, there's it's not so bad, because notice how Bob is sending the success or failure message to Carol here. So if I had not written that code in the choreography that communicates the result of that check auth request call, then there might be a problem. So different choreographic languages have different strategies for dealing with this. So some choreographic languages, if I had not included that first send in those at the beginning of those two different branches of the conditional, some choreographic languages would say this choreography is unprojectable and you must insert the proper communication to make it projectable. Other choreographic languages might just insert the necessary communication for you. That's actually what Haskell does. And this is both good and bad, because Haskell does it in a what we call a ham-fisted way, where it's just kind of indiscriminately inserting communication to all participants. We've also done some work on trying to make that more efficient in collaboration with Mako. And he's going to talk later about this. But this problem that I'm discussing here is known as the knowledge of choice problem, because it's the idea of these participants having the knowledge of which choice to take in this conditional. And so there have been different strategies for dealing with this. Implementing choreographies at the library level kind of imposes some constraints on the design space for how you deal with the knowledge of choice problem. And we're going to hear a lot more about that, I think, from Mako later on. So yeah, this is a good call out. Yeah, I wrote a choreography here that happens to be okay in terms of propagation of knowledge of choice. But if I hadn't done that, then we might have a problem.
I have a question.
All right.
I'll take the prerogative. So in the causal separation diagrams,
Yeah.
have you thought about them at all from a kind of software engineering or human factors perspective?
Mm-hmm.
So one thing I can imagine is, right, I'm trying to design some protocol or implement some protocol, and I can write my fancy Lamport diagrams on my whiteboard, and then I go, especially if I'm not doing choreographic programming, so I'm having to do all the projection myself. And I want to know, does this match what I had in my whiteboard? It might be really nice to be able to go, what's the visualization of this? Have you thought about doing that at all?
That's a great question. Yeah. So, I mean, I will say that CSDs are, so because they are formal, because there's this particular structure that they might follow, they are kind of a pain to write on a whiteboard and make sure you get the details right? So having done it many times, right, and having painstakingly made the figures in our paper, I know that you can get them wrong, right? So it would be nice to have some tools for automatically checking that. We have played around a little actually with, so in my student Jonathan's AGDA implementation of CSDs, so there's a textual syntax for CSDs, there's also a graphical syntax for CSDs. He played around a little bit with making the but implementing the graphical syntax. But right now, I would say it's still kind of a toy, and I think that there's a lot more to do there. So, and yeah, yet again, this is something that I would love for someone to pursue, and I would be happy to talk about it more later. In general, I love thinking about the semantics of diagrams, and I think I'm not the only one. So, yeah, great question. Yeah, Kieran.
Yeah, thanks for the talk. It was great. So I had one question. So this the CSDs were kind of introduced drawing from like Lamport diagrams, and I guess earlier in the talk you showed a sequence diagram, and inside the sequence diagram you had this kind of notation for branching.
Yes, right.
So I'm curious whether there's a sort of analog for CSDs.
Yeah, that's a great question. Yeah, so not yet. So that's actually, so this kind of relates to the earlier question about could CSDs be a program logic, right? I think to make CSDs into program logic, right, we would need to have branching and things like that. So yeah, there's no syntax for branching. We did actually experiment with it a little, and we came up with, what we call the choreographic CSDs. That experiment kind of fizzled out, and we were using these choreographic CSDs for a different project, and then we ended up taking a different approach for that project that we liked better. So that was kind of a, I'm not going to say dead end, I'm going to say unfinished journey instead. So yeah, right now there is no computation in a CSD. It's just one execution. But I don't see why there couldn't be. So I think that would be an interesting thing to look at. Yeah.
As somebody from the compilers camp, working extensively with Coral, is there anything that you're jealous of that we have that you don't have in the interpreters world?
Number of publications?
I think you're catching up to us.
Anything that we're jealous of? I mean, so, and Coral has, so obviously there's the work on fully out of order choreographies, and that's actually something we've been thinking about, but we kind of have our different twist on it. So I would love to talk with you more about that later, but it's not published yet, so TBD.
The ability of compilers to express.
Oh, yeah, sure. Well, I think that relates to like what I was saying earlier about how knowledge of choice can be hard to deal with, so people have So one thing that you can't do really easily with the library level approach is, part of the reason the talk is called Interpreters Everywhere is that you really do have to have an interpreter that has the entire program, right? On each of these parts, right? The interpreter has the entire choreography and will interpret it in a different way. So you have to have like a Haskell runtime on each of those endpoints. So that's kind of a necessary component of this library level approach. What if you didn't want to have that whole big runtime system? Or what if you didn't want to have to distribute the whole choreography to everybody? So some people have been working on ways to statically partition these choreographies. And there has been some interesting work on that. But I think it's kind of brittle. And so I don't think the problem is solved. So whereas with Coral, you can statically partition choreographies and just get Java programs, and then, well, I guess then you need the Java runtime, but presumably you have that already. So, I think like the static partitioning thing is kind of, how to do that. That's like being explored, but it's kind of an open question how to do it well or how to do it in a non-brittle way, and that's the big thing that comes to mind.
All right, I think we're out of time. Let's thank Lindsay again.
Thank you.
We are in the session for choreographic applications. I've got a lot of great talks lined up for you. If you are a speaker, I'd like you to stand right about here so that the camera can catch you as long as Mako isn't standing right in front of it. I think that's it. We can get right into it. First, we have Keith, who's going to be telling us about choreographic programming for supercomputers. Take it away.
About some joint work with my advisor Andrew Hirsch and another UB colleague Matt Nepoli. Specifically, we're bringing choreographic programming to high performance computing through the message passing interface, or MPI. Now, I expect you know some about choreographic programming, not about MPI. That's exactly where we're going to start. Importantly, for the next 20 minutes, this is not the Max Planck Institute. This is the message passing interface. Okay. So, what is MPI? MPI is the default standard for high performance computing, or HPC. I say it's the default because it's being used everywhere in medical, aerospace, and energy research. It does things like simulate the possible spread of COVID so we can help better combat it. It's doing things like launching humans around the moon with the Artemis II mission. It's doing things like setting the next generation of nuclear safety standards at the Argonne National Lab. So everybody's using it, or something derived from it, but everybody's using MPI. And importantly, MPI is not a language, it's a library specification which is then implemented in different languages. Typically things like C, C++, and Fortran, but there are also implementations in OCaml, which we'll see later. But for the most part, we're thinking C and Fortran on clusters and supercomputers. Okay, we have to learn a little bit more about the specifics of MPI to sort of talk about what makes it really interesting. So to start with, we're going to talk about groups. So we're working with clusters. We have lots of processes or nodes which are going to be using interchangeably. Now let's consider a system of 8 nodes. Now, if this is our entire system, this will form a group, the global group, and groups are just logical collections of processes. So in our group, every process has a rank or its name. Importantly, these are sequential integers starting at 0, going to n-1 for a group size of n. All right. And importantly, you only have a rank, you only have a name in the context of a group. So you're only 0 in this group. You're only 1 in this group. Now, sometimes I don't want to talk with the entire group, like I am right now. Sometimes we want to split off, like when we go to lunch. And for that, we can make another group. So we can now organize what were global 4, 5, 6, and 7 into a new group, where they are now 0, 1, 2, and 3. And we can do this pretty much as many times as we want. We can build groups out of any of our processes. This is really nice. The other important thing to know about groups is that 0 is the root of a group, and sometimes it has a special job. Alrighty. Groups are important because they show up everywhere. All communication happens within the context of a group. Remember, you're only 0 in a group. So when we want to do point-to-point communication, 2 nodes sending messages to one another, we have to talk about it within a group. So if I ask 0 to send to 1 in the black group, our global group, and I peel back the curtain, that's really blue nodes 0 and 1, because it's the global group. Okay. However, I can ask the same thing of our red group. In the red group, I want 0 to send to 1, and now when I pull back my curtain, I'm instead talking about 4 and 5. Okay. But the MPI developer said, you probably don't want to organize 1,000 nodes with point-to-point communication. Let's give you something a little more powerful that you can use, and we have a couple collective communication operations we need to use. The first is broadcast. So in a broadcast, your root, this is where they have special jobs, is going to send the same information to everybody in the group, including itself. So 0 takes its piece of information, and everybody ends up with a copy. All right. That's great, but sometimes we want to do distributed computation, where everybody gets a piece of the puzzle to work on. And for that, we're going to need scatter. So scatter is going to split an array into equal-sized pieces and send a piece to everybody in the group. The piece of the array you get corresponds to your rank in the group. So 0 has its array, it splits it up, and everybody gets their piece of the problem to work on. Alrighty. Once we do our computation on those pieces, we want to collect it back. And for that, we're going to need gather. So gather is going to take a piece from everybody, send everything to the root, and the root is going to organize it back into one array. Again, the order of this array is determined by your rank in the group. Okay. That should be more or less all the information we need for MPI. If anything else comes up, don't worry, I'll let you know. Okay. So now we have 2 questions to answer. One, is deadlock freedom of MPI programs important? This is choreographic programming, so when we're talking verification, we really care about deadlock freedom. And the answer is yes. MPI programs are answering important questions, and they're really expensive to run. Time on clusters isn't free, and it's not cheap. So you want to make sure your program doesn't get stuck and you have to run it again. All right. Our next question is, well, why choreographic programming? Why is this the vessel to talk about deadlock freedom for MPI? And the answer there is, well, MPI programmers are already doing pseudo-choreographic programming. What's that mean? Well, let's look at what it means to write an MPI program. In MPI, you write one global program, and then this global program is run at every node in your cluster. So everybody runs a copy of your program. This means if you want to specify behavior for a specific node, say 0 of the global group, you're going to be using big if then else statements. This is very similar to choreographic programming, where again, we start with a global program, but instead of a copy, we project. So we project into individual programs for your different nodes in the system. Okay. So MPI programmers and choreographic programmers are all starting at the same global program idea. It's even more similar when we look at specific programs. Before I show you any actual MPI code, it's verbose. I apologize. And also remember, we're typically working in C and Fortran, so everything is numbers. But we'll get through it, I promise. OK, the first thing to notice is this big if then else branch. This is what I'm talking about. If you're 0, run this code. If you are 1, then run this code. What are you doing if you're 0? Well, you are sending to process 1 of MPI COM world. MPI COM world is just your group. It's the global group that we were talking about. All right, and importantly, the other half of that, if you are 1, well, you better be receiving from 0 of the global group. OK, so there's a lot up here, but we can make sense of it. All right. On the left-hand side, we're going to see a little bit of the choreographic and network language. We'll talk more about them later. But to start with, as choreographic programmers, we see these separate sends and receives, and we want to piece them together. And we can do just that. Before we do that, for brevity, I'm going to call MPI COM world G. So that's going to show up. But we can piece our separate sends and receives together, and we end up with the same information. So within this group, 0 is sending the message data to 1. Alrighty. And then when we project it out, we see this separate send and receive that we saw over in MPI. So MPI programmers are almost thinking about projection on their own, and I don't want to do projection on my own. I want the computer to do it. All right. The story is even more similar with collective communication. In MPI, when you want to write a broadcast, every process in the group has to write this expression, where you're broadcasting data to this global group. Importantly, this is different, or interpreted differently, if you are the root or if you are not the root. If you're the root, that says, hey, I better send to everybody. And if you're not the root, that says, hey, this is going to be a receive from the root. Not literally, but this is how it behaves. OK. And this is very easy to translate into a choreographic world, where again, we're just broadcasting data to our global group. So hopefully you're convinced. And that leads us to what we're doing. Well, we are writing core MPI. It's a choreographic HPC language based on MPI to ensure deadlock freedom. 2 caveats here. Based on MPI. Why that? Well, we're working with a functional subset of the MPI standard. The MPI standard is 1,200 pages long. We cannot capture all of it, but we have a core message passing part of it. We feel confident of this because we're working with Matt Nepoli, the other collaborator here. He is a core developer of PETC, a well-known HPC library that supports things like MPI. So he has been instrumental in helping us decide what parts of MPI to focus on and what is the MPI standard actually telling us to do, because the MPI standard is all natural language. OK. So now we get to talk about languages, the actual languages for this project. We're going to start with a network language, so Lambda MPI. As its name suggests, it's Lambda calculus. In fact, it's a concurrent Lambda calculus. Some of the interesting things about Lambda MPI are the same things that make MPI interesting: point-to-point communication, collective communication, and extensive group calculus. So again, we have our sends and receives we saw before. We have broadcast, scatter, and gather as primitives. And then we have just a handful of our group operations. I would love to talk more about the groups and the group calculus we've come up with, but I just don't have time today. So if you want to hear more about that, find me another time. It's really interesting. All right. This is cool, but it's more than just what we're going to project to. Lambda MPI also gives us a nice model of MPI. That 1,200-page MPI standard written in natural language is hard to work with. This gives us something to do math with, which is much nicer. And of course, we are also working to mechanize proofs about this language in Rock. This is a work in progress. This is also how I'm learning Rock. So this is going fairly well. Alrighty. Now, finally, the choreographic language. So core MPI, it is our work in progress choreographic language. And to start with, let's just see how we can go from the network language to our choreographic language. So again, these mismatched sends and receives, put them together. all of our collective communications look very similar. We are broadcasting, scattering, and gathering, each their own type of communication. All right. But we have a problem. What does it mean to scatter to something? Well, we know what it means, but how do we actually talk about everybody getting a piece of that information? And then importantly, what do we do with that information once we have it? And for that, we need to introduce two new things, the faceted value and the SIMD block. So we're going to start with the faceted value. This is a term we are borrowing from the information control community, or information control flow community. So a faceted value is just how we talk about what piece of the array everybody's going to get. So all of these different expressions are what each individual process in group G is going to get, and they all better have type T. I like examples. We're going to start with a 4-process group. The only thing you really need to know about this group is it has 4 processes, so all of our faceted values better have 4 expressions. All right. So the first one, we can give everybody an array of natural numbers. And the second one, we can just give everybody a natural number. So these faceted values do look a lot like arrays. We have a pretty good idea of what we want to be sending. All right. But importantly, if you are the root of this group G, our first faceted value to you just looks like the array 0, 1. So that's all you really need to know. And importantly, again, this just looks like 17, which is a natural number. So from the view of 6, your big faceted array is really just what it needs to know. OK, so that's how we talk about getting the information to different processes. What do we do once we have it? For that, we need a SIMD block, which really cares about 3 pieces of information: a group, a faceted value, and then an expression E. So this expression E is going to run at each of these processes P in our group G. And each of these individual processes is going to have access to X, which is its piece of the faceted value, its piece of what you probably scattered. OK. Importantly, the SIMD block results in another faceted value. OK. Again, I'm a big example person. Let's see these in action. So this is the roll call example. We're going to take an array of zeros. Everybody in the group is going to get a 0. You are going to add your rank in the group to it, and then we are going to collect all of this back at the root. OK. First thing we need is a group, so we'll start there. Back to my favorite group. Importantly, we care that it has 4 processes. All right. Our first actual communication we want to do is scatter. So we are going to scatter. So this is our scatter expression. Importantly, we are scattering this array of zeros, which is located at the root of G, which is always going to be rank 0. Everybody's going to get 1 0 from this scatter. And again, just G again, because we need to talk about what group we're in. And we're going to call this faceted value, because we're going to use it later. We're going to use it right now in our SIMD block. So once we do our scatter, we have our SIMD block. So it says, well, for everybody in our group G, you're going to take your piece of the faceted value. You're going to add your rank to whatever you get. This a.get is an array. We have to scatter and gather in arrays. It's a little onerous, but remember, we're working in C and Fortran, and over there it's buffers. So it could be worse. So we get arrays, they get buffers. All right. So that's just getting the first thing from your array X, which in this case is always just going to be 0. All right. And that's what these square brackets on the outside of it are for. We have to package this back up into an array. All right. So we've scattered our value. We've done our computation. Last thing to do is just gather. And that's all we are going to do. Remember, gather is going to take a faceted value, which is what SIMD is going to result in. Everybody is going to send one thing to the group. And overall, this will give us our roll call example. This gives us a very common pattern that HPC people are looking for. OK. That's a little bit about the language, mostly just some of the communications. Again, it's a work in progress. But I do want to talk about some things we're excited to explore as we continue on with this. So the first is multiply located in SIMD values. So what are multiply located values? Well, that's what we end up with when we broadcast. So in a broadcast, everybody gets the same value. We know what everybody in the group has. I'm not going to talk too much about this because Mako's going to tell us a lot more about multiply located values, I think, later, more or less. I'm going to leave it to the pros. But again, this is not our idea. This has been seen before in languages like he lambda small and lambda quick change. The other exciting piece of this puzzle is SIMD data, so single instruction multi-data. This is what we're working with scatters and gathers. We just saw it in our example. This is why we added things like the faceted value. As far as we know, the only other work to tackle these is Symphony, a language for secure multi-party computation that, when trying to describe some of the more complex computations, ended up pretty much back at choreographies, which is really exciting. So, alrighty. Next up of things we're excited about is endpoint projection. We're hoping to explore two types of endpoint projection. The first is exactly what you're thinking of. I take my global program and I project it into individual programs like we always do. And that's great, but we also want to explore the possibility of taking our global program, projecting it to one Lambda MPI program, and then having everybody run a copy of that program. The idea here is we still get all of the nice choreographic reasoning with our global program, but it's much more similar to how MPI operates, where everybody's running the same program. There's also hope this could help with scalability. So if everybody just gets the one program, life is easier. Okay. The last thing we're excited about today before we wrap up is we're working on a compiler project with 2 undergrad interns this summer. So they're writing a compiler to take core MPI, project it into Lambda MPI, and then finally compile to OCaml with MPI bindings. This is where OCaml shows up. I know what you're saying. Keith, I'm probably not going to be rewriting my MPI in OCaml. Some folks are, and that's great, but most people are not. Again, we're typically in C or Fortran. Our goal is to show that adding core MPI, projecting to Lambda MPI, compiling to another language is not adding a bunch of overhead, and we can actually replace OCaml with things like C or Fortran at some point. Okay. So, to sum it up, we have unverified MPI code answering really important problems, literally doing rocket science. But they're already sort of doing choreographic programming. So with a few extra steps, core MPI, we can ensure deadlock freedom without really interrupting their workflow too much. And we're really excited about this. We'd love to talk to you about this if this is something you've thought about, if you have ideas, if you have feedback, anything. I would love to talk to you guys about this. And with that, that's the end of my talk. I would love to take any questions.
Hi, thanks for the talk, and what a fabulous motivation for choreographic programming. Could you say maybe just a little bit about those operators that you teased about?
Yes, absolutely.
Yeah, and particularly, is the number of your participants fixed? It looked like you had a union operator.
Yes, so we'll talk a little bit about groups, and I do actually have slides because I was hoping people would ask.
You baited me well.
I did. So things to know about groups. In our model, at least, we have three classes of defined groups, or sort of predefined groups. We have that global group we were talking all about, the empty group, and then singleton groups, so groups with just one process. And then we can use our constructors to build all the other groups you want. Importantly, what makes our group calculus interesting is it's a little different from MPI's group calculus. MPI uses union, difference, and intersection, which work more or less how you think they do with sets, but with some extra ordering, because groups have an ordering component to them. We have union, just as they do, but we also have split and shuffle, which I have a couple quick examples if you're an example person. So splitting says, hey, I want to take my group, split it by some function, and this is going to end up with an array of groups we get to talk about. And then shuffle is just permutations of the ordering of that group. And these let us express all of the group constructors in MPI, which there's more than just the 3 I showed, but with the same, just with our 3 constructors. We are working with a fixed number of processes, but you can union groups. So we're not creating more processes, we're just unioning the groups we already have. Okay. Hope that's a nice little overview. Yes, or who has the mic? You have the mic, sorry.
So groups in the sort of Lambda MPI or Coral MPI, choreographic MPI seem to be a combination of communicators and groups from MPI. Right, because groups in MPI are unordered, right? Whereas communicators are ordered. So, is there a sense of ordering in your version of groups? Or?
There is. This is another important caveat. In MPI, all communication happens within communicators, one type of which is groups. Groups are the only one we are supporting. When you really get down into it, our groups are sort of a bit of a merging between communicator and MPI in many ways. But there is ordering, absolutely.
We have time for one more short question and then for a set up.
Okay.
So regarding the syntax of the SIMD instruction, you had that inner body expression E. Can that be a whole program, or is that limited to a sub-expression language?
I don't know.
It's a local program.
Yes, it's a local program.
I don't know that we have any restrictions on it other than, you can't communicate because it's local.
Yes, so probably not communication. something I took out of this talk, but as I was writing it, the last part of this talk I actually wrote was the core MPI example stuff, because that is the newest stuff we're working on. I think we started thinking about the SIMD block stuff, I think 2 weeks ago. So very, very much work in progress. I'd love to talk more about it. Yeah.
Let's thank the speaker again.
Thank you.
And now we have Jennifer, who has just joined University of Vermont as an assistant professor. She'll be telling us about quantum choreographies. Take it away.
Great. Is working? Sounds like it. Okay. So we said in the beginning of this workshop that something like 70% of the people here were relatively new to choreographic programming. I am definitely one of those people. I mostly work in the intersection of programming languages and quantum computing. So in the past, I focused on like type systems and compilers and so on. And so this is the point where I tell you that quantum computing is a really exciting, rapidly developing field, and it's going to drastically expand computing capabilities, blah, 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 blah. And I'll get into a little bit of what quantum computing is in a little bit. But one of the main challenges is that our quantum computers of today are very small, among other deficiencies, maybe between 10 to 1,000 quantum bits, qubits per device. And so distributed quantum computing is really gaining popularity as a way to expand that computing power by networking devices together. There are sort of other applications, though. In addition to distributed quantum computers, we might also consider distributed quantum networks more generally, like a big quantum internet that allows for communicating both classical and quantum information across long distances, and for enabling secure communication with quantum cryptography. So I was talking about sort of the idea of distributed quantum computing with Joe and Chris, my collaborators. And we were looking at a diagram that looks something like this. So this is a circuit representation of a quantum program. And you don't really have to worry about what these different operations are, but it's a very informal. It's very, very similar to those to the timing diagrams that Lindsay was talking about, and so Chris and Joe looked at this and said, "Yeah, this looks like it might be a really good application of choreographic programming." And I said, "Oh, what's that? Never heard of it." So today I am going to try to convince you that, yes, this is actually a really great application of choreographic programming. It's not trivial, though, and it introduces a lot of really interesting design questions due to the constraints of the quantum programming model. And so I'm really interested in feedback into these kinds of constraints and how they show up in different settings. So with that in mind, I'm going to start with a very high-level overview of what is quantum computing, what is distributed quantum computing, and then we'll talk in a little bit more detail about the different design decisions that have come up as we've tried to build this system. And finally, I'll end with a little bit of a teaser towards work in progress for an implementation of quantum choreographies, which we call choreo. Okay, so main idea of quantum computing is that rather than bits, which for any non-quantum things, I'll sometimes call them classical. So rather than classical bits, 0 and 1, quantum computers deal with superpositions of classical bits, which we call qubits, quantum bits. And so the idea of these superpositions is that this qubit is sort of in both the state 0 and 1 at the same time. And we can manipulate these qubits in a variety of ways. One way is by measuring them. So when you measure a qubit, we're going to collapse the state of that superposition into one of the classical bits, 0 or 1. And this is a probabilistic operation, and the probabilities depend on the state of the qubit, et cetera, et cetera. There's other ways to transform qubits as well, which I'll refer to as unitary gates. We don't have to care about what these are. They're described by a certain class of unitary matrix operations, so that's why they're called unitary. But all you need to know is that they transform the state of a qubit without measuring it, without collapsing it. So where quantum computers become really powerful is when you have multiple qubits in a system. So if a single qubit is a superposition of 0 and 1, an n-qubit system is a superposition of all length n bit vectors. So there's sort of like an exponential representation going on here, right? N qubits can somehow talk about 2 to the n different bit vectors, or a superposition of those. And a really important concept when we're talking about multiple qubits is the idea of entanglement. Informally, this just means that 2 qubits are entangled if the state of one depends on the state of the other in some mathematically formal way. And an example of this is what I'll call the Bell state, which is a pair of qubits which may be both the state 0 and they may both be the state 1, but there is no probability of one of them being 0 and one of them being 1. And so if you were to measure the first qubit, for example, and you get a 0, then you automatically know that the second qubit is also a 0, even if you haven't actually looked at it. Okay, so this is quantum computing 101. You passed the class, great. When we talk about distributed quantum computing, we've got all the same ideas, plus we have different physical locations. I'm going to refer to these as actors. And one thing to note about these systems is that the quantum state is global. So in particular, different actors might have entangled qubits together, and so you can't just look at the state of one actor system independently. You have to look at it all in the same context. And so what do we do in a quantum distributed system? Well, we can do 2 things. There's a form of quantum communication, which the only thing you can do is to establish an entangled pair of qubits between 2 distinct actors. And so this idea of entanglement generation is what I want to think about of what quantum communication is. We'll talk a little bit more about this as a design decision, but this is sort of the established primitive of quantum networks. This is like what these networks will provide. And then in addition, we will also allow classical communication, where you can normally send and receive classical data. But of course, those can't be qubits. Those can't be quantum data. Okay, so I want to give, let's give an example of a distributed quantum protocol. And this example is going to be quantum teleportation, which is sometimes referred to as the hello world of quantum computing. And so the idea here is that Alice is going to start off with a qubit in some state, and by the end of the protocol, we would like Bob to have a qubit in that same state. So what we're not doing is we're not taking the physical particle that represents the state of the qubit and moving it to Bob. We're assuming that these are far away distances. So we need to figure out how to communicate the information of the qubit using a protocol. And so, okay, well, I could write this out as a circuit diagram like I showed on the first slide, but I think what I'm going to do is just show it as a choreography. And so this is syntax in Choreo, which is our work in progress implementation, which is a domain-specific language embedded in Rock. So you can focus in on Rock syntax if you like. So I'm going to write a function, teleport, takes in 2 actor names, Alice and Bob, and Q, which is a variable that's going to be located at Alice. And okay, so the first thing that we're going to do is Alice and Bob are going to establish an entangled pair of qubits. And those are called A and B. Then Alice is going to perform some local operations. So I'm just using the syntax for Alice's local operations, and these are quantum operations, right? So we've got some unitary operations that transform qubits. We've got some measurement operations which are going to collapse the state of a qubit, and the output is going to be a classical bit, x and then z. And then once we have those classical bits, Alice is going to send those to Bob, right? So we've got some classical communication going on. And then finally, Bob is going to do some local operations to his qubit using those classical values. I'm not going to explain why this protocol works, but this is the protocol. Okay. And so as I said, this is often described, like written down in a circuit diagram like this. But of course, this is informal. And so if you wanted to actually program a quantum distributed system or even simulate it, you would write in a process representation. There's been plenty of work in quantum process calculus and things like that. I have some informal syntax here. Well, it's not informal, it's the representation of processes that we have in Choreo. And of course, the challenge of the process representation, as you know, in classical process calculi, is the synchronization of communication primitives. Right. So in this situation, it's very simple. We've got this might be hard to read. I apologize, but we've got we want to establish the entanglement, so the quantum communication, and then we need to synchronize the classical communication as well. So, okay, choreographies to the rescue. These processes are, of course, just the result of endpoint projection of our overall choreography. Okay, great, easy, works out fantastic. Let's talk about some of the sort of challenges and design decisions that have come up when we're thinking about how to design and formalize this language so that endpoint projection is actually safe and correct. So the first thing to note is this idea of quantum communication being entanglement generation. And this is kind of like a weird idea, right? So in classical, you know, in the regular send and receive style, regular COM operation, we have a directed operation. And this entanglement generation, for one, is undirected. And of course, you might ask, well, why don't we just have this quantum teleportation idea as the primitive, right? I just showed that you can communicate quantum states from one actor to another. So like, why isn't that the primitive operation? And the answer is that there are other kinds of high-level communication primitives, or not communication abstractions, like just like applying a distributed gate over multiple actors, for example, that really are based on entanglement generation and not on quantum teleportation. And so really, and also a lot of work on like routing entanglement generation and processes for entanglement generation, those are sort of the foundation of these quantum network systems. So there's some arguments that maybe we want teleportation as an abstraction, but I'm going to make the argument that really it's entanglement generation that is the foundational notion of quantum communication. Another constraint that you might not think about is the use of the difference between quantum data and classical data. So classical data, right? When we can reuse it arbitrarily. So even though you send, even after you send some classical data to Bob, and then you send classical data, you send that same data to Charlie, and then you can still use it to compute things and so on and so forth. That is not the case for quantum data. So there is a principle called the no cloning principle of quantum computing, which says that the state of an arbitrary qubit cannot be cloned or duplicated. And so a consequence of that is that you cannot apply a quantum function to the same qubit twice. In addition, if you measure a qubit, I said that it collapses the state of that qubit, right? So it kind of doesn't make sense to still have that qubit around after you're measuring it. So it's kind of like a use after free type of situation. So the typical way that non-distributed quantum programming languages deal with this besides ignoring it, but the formal way of dealing with it is to have linear or other substructural type systems for these quantum programming languages. And so this is an important component of our choreographic language, is to layer linear types on top of these choreographic programs. So there's one more point, which is more of a meta-theoretic question about choreographies. So in classical choreographies, let's say we have Alice and Bob, which are not blocked on any communications. They can take steps independently. And we know that it's safe in the choreographic model, or at least in like the standard choreographic model, that the processes are independent. So Alice can take a step to A prime, and then Bob can take a step to B prime, and that's going to be the same as if Bob took a step first. In the quantum model, these processes are not independent, right? I said that they share a global state, and so potentially the state that, so if Alice takes a step first and let's say measures one of their qubits and gets an answer, then the possible step that Bob can do might be different than if Bob had gone first. Okay. So they're not independent. However, don't worry, everything's fine, because even though they're not independent, they're still complement. So there's it is easy to reason that, and it's well known that whether if Alice and Bob operate on separate sets of qubits, which means that there's no communication going on, even if they're entangled, then they can still happen in either order, and you're still going to get an equivalent quantum state. Okay. But there's a little subtlety baked in there, which is that this operational semantics for these quantum processes are also probabilistic, right? I said that measurement is probabilistic, so it's going to collapse your state to either 0 or 1 with some probability. And if you've ever worked with a system that has both probabilities and non-determinism before, it is a mess. So it would be really great to not have to do that. And guess what? Don't worry. We can avoid, this probabilistic effect in global state. We can also avoid that. So in fact, quantum programming languages in general tend not to use a probabilistic semantics to reason about their behaviors. They tend to use a different representation called, which are referred to as density matrices or sometimes partial density matrices. And the basic idea is, high-level idea, instead of a probabilistic step relation on quantum states, we have a non-deterministic step relation on what is essentially probability distributions over states. And there's other benefits of this representation as well. So we all sort of win. So by using this representation, okay, now we have a non-deterministic semantics over these probability distributions, but that's all good because non-determinism and other non-determinism is just fine. They go together quite well. Okay. So with all that in mind, I showed you the example of syntax of the choreo language, which is this work in progress that I'm building, also with the help of a grad student, Stephen, who I forget his last name right now. Oh no. What? Stephen Baldowski. Thank you. Yes. And so the layout is as follows. We have a local quantum language that has a linear type system, and we've proved type safety and all of this. And this is embedded in ROC, so these are formally verified proofs. And then we define endpoint projection as a function to a sort of embedded process calculus. And then we also have kind of an extraction or another compilation layer to netchasm, which is a representation that is more widely accepted by quantum network simulators and potentially real quantum network systems. So I'm very excited about this application. So not only just having a choreographic quantum programming language to do this programming in a safe and secure way, but one thing that I'm really interested in that I would love if anybody else has thoughts on is the idea of using these choreographies as intermediate representations. And so in the context of choreo, right, I can imagine having a sort of high-level version of the language which has some higher-level communication primitives. So maybe at that level, the communication primitives would include quantum teleportation, but also distributed gates, and so on. And then that can be compiled to a version with the entanglement generation primitive, and then that can be extracted to processes. And I think that each of these different layers enables potentially different kinds of optimizations, whether that's at the application layer, whether that's at the sort of network layer, or at the actually like local process layer. So I'd be really interested if folks have thoughts about that. And with that, I think that's all I have. Thank you all so much.
Thanks. Thank you for the talk, and welcome to the choreographic programming community. It's good to have you here. So I have a noob level question about distributed quantum computing. So you showed this quantum teleportation example, and it seemed like it involved both quantum communication and classical communication, right? So the get entangled pair is kind of the quantum communication is happening there, right? And so I guess my question is it generally true that to do distributed quantum computing, you need both quantum communication and classical communication? Or do people ever have like quantum computers that are connected by a classical network? Like, would there be a reason to just do that? Or you know, would that be useful? And I guess the reason I ask is, you know, I find just classical networks, you know, complicated enough. So, you know, so I guess I'm wondering, is there any reason or advantage to doing it that way? Or do you need to also do quantum networking if you're doing quantum computing?
Yeah, I think there's definitely applications for having quantum computers just connected via classical networks. One application that I am definitely very interested in is hybrid quantum computers, where it's actually not exactly that situation, but you have a quantum computer and you have a classical coprocessor. And the quantum computer will, you know, maybe send instructions or parameters to the quantum computer, and the quantum computer can only send back measurement results. And the interaction between those two can be quite non-trivial. So that's maybe one application of that. But I think that there's also protocols that only use that. I mean, you can think about applications of quantum computers that are just communicating with each other. There's things like circuit cutting. So yeah, absolutely.
We have time for one big question while here sets up, or maybe two small ones.
So I maybe this is the same as Lindsay's question. I'm not entirely sure, but this entanglement primitive seemed kind of magical to me, right? Because suddenly everybody can entangle with everybody without communicating. Is that physically realizable, or is there something else going on under the hood that would be good to model?
Yes, there is an entire network infrastructure that is required in order to enable that get entangled pairs between arbitrary actors. And they need to be, you know, connected in the network and so on and so forth. And so I think that is a really interesting question. It's definitely a very important question for like finding good routes through the network and so on. And there could even, you know, whether choreographies are the right thing to model that, I'd love to like brainstorm about that. But reasoning about that like network layer of establishing entangled pairs, there's a lot going on there. So Robert Rand has some really good work about that. Yeah.
Okay, let's thank Jennifer again. And next we have Kieran from the Basis Institute, who's going to be talking about the overlap of choreographic programming with game theory. Take it away.
Awesome, perfect. I'm Kieran. I'm a research scientist at the Basis Institute, Research Institute. It's a small sort of non-profit research institute based in New York. And today I'm going to be presenting about this work on behalf of my collaborators called Packed Choreographic Languages for Agentic Ecosystems. And quickly, before your eyes glaze over, I just want to say this is not like about LLMs. So, pay attention. This is like really fun stuff. I'm really pleased to present this to you all. But before we begin, a sort of small amount of motivation. So, for better or for worse, and maybe for worse, we seem to be very rapidly heading towards a world populated by sort of these ecosystems of agents talking to each other. And so one of the questions that we, is going to become increasingly important as we move forward is whether we can trust these systems of agents talking to each other. And obviously, yeah, it seems not really. And unfortunately, it seems with the current state of the art, the main medium by which agents sort of communicate is through natural language. So if I had sort of two agents and I wanted them to sort of talk to each other and maybe conduct some kind of transaction, then the way this would operate is pretty much through the agents sort of talking to each other in natural language, in English. And they just chat. And so this transaction would occur in a purely sort of ad hoc, informal and unstructured way. And if you've been sort of following the news, or you may have seen any number of sort of somewhat humorous, maybe somewhat depressing stories of these agents going awry and sort of doing various kinds of incorrect things. So overall, these things are very vulnerable to even basic, very dumb things like prompt injections or coercion, and sometimes they just do the wrong thing entirely. And at a high level, the issue here is that natural language as a communication substrate really provides no guarantees on the kind of protocols that they run. So this is kind of the motivation that led us to sort of look into this problem. And the question that we were trying to sort of investigate was whether we can use sort of choreographic languages as a formalism to enable trust in these kind of agentic ecosystems. And in this process, we kind of landed on a rather nice place in the design space that has sort of pretty much nothing to do with LLMs at all. It's rather nice sort of unifying of these ideas from choreographic programming and also economic game theory. And that's what I'm very happy to present to you today. So the sort of rest of the outline of my talk is as follows. I'm going to first start off by sort of motivating how choreographies kind of fall flat in these untrusted ecosystems. And then I'm motivated by these failures. We're going to look at how we can extend a sort of basic choreographic language to incorporate notions of game theory. And then the third thing we're going to do is using this interpretation as a game theory, as a sort of formal game, we can actually treat endpoint projection as a means to do sort of decision policy solving. This is kind of the bread and butter of game theory. And finally, I'm going to conclude with some directions for future work that I'm interested in looking into. I'd love to hear any of your comments and criticisms, or maybe collaboration if anyone is interested. So without further ado, let's dive in, starting with the limitations of choreographies. So to kind of motivate this, let's look at the sort of the bread and butter of choreographic programming, and that is the bookseller protocol. So the high-level idea, as I realize, I guess from the intro talk, not everyone here knows choreographies. We have these kind of two participants. We have a buyer and a seller. The buyer would like to sort of purchase a book, and the seller would like to, I guess, make a profit and sell the book. So using a choreographic language, we can represent this in a concise, sort of nice, elegant, global perspective. So the choreography describes how this transaction should proceed. So starting off with the buyer is going to send their title over to the seller. And so once the seller kind of receives the title of the book the buyer would like to buy, the seller is going to perform a sort of local computation. They're going to work out, given the title, what price they want to set for that book. And then they're going to send that price back over to the buyer. And once the buyer received this price, the buyer is going to then do their own local computation and decide whether they want to accept. So for example, whether this price is within their budget. And if they do decide to accept, then we can sort of send this over to the seller and we can conduct a transaction. So all in all, a pretty nice, clean and elegant description of this sort of protocol that several talks prior have demonstrated are substantially more concise than maybe writing the individual programs. But this standard choreography kind of falls flat if we want to sort of run it in an untrusted ecosystem. And that's because it kind of overlooks one sort of core question that arises in these settings. And that is, why would buyer or seller actually want to follow this protocol? Right? In some sense, the choreographic protocol is overly prescriptive in the sense that it dictates what the local computation should be. And you can think in sort of an untrusted ecosystem, there's no way that the choreography can actually enforce what an agent does locally, right? You can think sort of maybe a strategic or unethical seller might actually choose their prices based on maybe a prior belief about the buyer. Maybe if the buyer is rich, we can get away with charging them more. And similarly, a strategic buyer might decide to accept lower prices if the seller is kind of desperate to get rid of the book. And so the question that this kind of raises is, how can we reason about these kind of strategic interactions between these conflicting objectives in a principled way? And as it turns out, there's an entire field of research whose bread and butter is exactly answering this kind of question, which is formal game theory or economic game theory. And so the core of this idea, of this work, is to sort of investigate whether we can actually bridge between these two formalisms, whether we can take choreographic languages and we can somehow map them over to formal games. And this brings us on to the next part of the slide, which is how we can actually map a choreography or extend a choreography to correspond to a formal game. And as it turns out, we can do this in sort of 4 simple steps. So let's take a look at our initial sort of buyer-seller protocol that we walked through earlier. So the first thing that we want to do is, so how can we turn this into a game? The first thing that we want to do is we want to take the local computations that we've already said are sort of overly prescriptive, and we want to sort of change those into agent decisions. In particular, there's no way of enforcing that an agent is going to run a particular local computation. So to really be faithful to what's actually executing at runtime, we should really treat this as a sort of a non-deterministic choice. And in a game theory parlance, this would be sort of agentic. These would be sort of decisions where each of the participants can make kind of strategic actions in conformance with kind of like the types that are required. So in this case, choosing a price or choosing whether to accept. The next thing is, now that we've expressed these agent decisions, we need to reason about what are the factors that influence what decisions an agent would take. And in this case, the utility of a seller in this protocol is kind of explicitly encoded. The seller gains the monetary value of the transaction. But what about for the buyer? So in this case, the buyer's profits are kind of implicitly described. The buyer receives the book, but there's no real sort of explanation of how this translates to a kind of quantitative utility. So the next component that we want to extend is we want to extend this language to include sort of declarations of utility. In this case, this value statement declares that the buyer's utility in this game is kind of a function of this property of the quality of the book. And so now our choreographic language has been extended to explicitly describe the utility of all participants. Now, the other thing to think about is the quality here. Where does that come from? This is kind of a property that is of strategic relevance to the game, right? The utility of the buyer is going to depend on the quality of the good that actually gets sent over. But it isn't something that any of the agents actually choose. The book has a certain quality that's kind of pre-described outside of the game. So the next thing that we want to do is we want to take any exogenous variables like this, and we want to the game theory parlance here is to kind of treat these as nature variables. These are kind of dictated by the world outside of the game, but these are relevant for the sort of the game that we're playing. And the final, and the quality is kind of an assumed prior about the world. So when each person or participant interprets this program, they're going to have to apply their own priors about what they believe the distribution of quality of these books are. And so now all of the exogenous variables in this game are explicitly described as well. And the final component that we need to modify is just in this transaction. If we're running this in an untrusted environment, this has to be a sort of atomic step, because I could sort of send you the money and you could walk away without sending me the book. So really we need some sort of language primitive for atomic exchanges between participants to really capture a game faithfully. And in theory, you could see this as being built on top of various kind of distributed consensus protocols if you wanted to implement this in a distributed system. So with this, now we have this choreographic language that has been extended to formally map to a sort of game theoretic game. And to kind of like consolidate this mapping, we can actually take this choreographic program and we can map it in a mechanical way to sort of notations from game theory. And in particular, I'm going to map it to this notation called a multi-agent influence diagram, a MADE diagram, or a MADE graph. And we can do this sort of mechanically. So we can take any of the agent decisions, and these will become sort of decision nodes, colored by the participant who is making the decision, and the edges represent dependence. So in this case, the buyer's decision to purchase the book will be dependent on whatever price the seller sends. And you can work this out sort of automatically using a sort of information flow analysis over the choreographic program. Next, for any sort of utility and exchange of sort of funds, we can represent that as utility nodes, again, using a similar information flow analysis to work out the dependence between these different decisions. So the utility of the seller is going to be dependent on what price they set, and similarly for whether the utility of the buyer is going to be dependent on whether they decide to purchase the book or not. And the final component is we can take any nature variables, and we can represent these as sort of nature variables. So they also influence the outcomes of this game. And so with this, our choreographic program now corresponds one-to-one with a sort of formal game theoretic game. And so why is this useful? Well, game theory is all about sort of answering questions about expected payoff, and in particular, things like how should I choose a decision policy, right? This is kind of a specification for an interaction, but I haven't really specified how agents are going to make these decisions. And if we map it to a formal game, we actually have a principled way of answering these kind of questions. So this brings us to sort of the third part of this talk, which is how we can use sort of endpoint projection as a means for decision policy solving. And I think this is kind of like the coolest part of this work. So I'm really excited to talk about this, but I just want to say like this is going to be a little bit, it's going to be a little bit subtle, a little bit like kind of mind-bending. So just be prepared. Okay, so consider that you are a buyer participating in the bookseller protocol. So you're participating with some seller. You send over the title of the book that you'd like to buy. The seller sends you back a price. And now you are faced with making a decision, right? I need to choose whether I would accept this price or I should walk away from this transaction. And so how should I work out whether I should accept this price? So game theory tells us we should accept this price if our expected utility from this transaction is going to be positive. In that sense, this seems like a good idea. But really, the utility of the buyer in this transaction is going to be a function of the quality of the good, right? So the question really boils down to, well, what is the quality of this good? Now, unfortunately, as you may have noticed, the quality of the good is something that only the seller knows, right? As a buyer, before I purchase the good, I don't really know if it's good or bad, at least in this transaction. And so the question then devolves into something of, well, how did the seller choose the price, right? The only information that we know is the price the seller has given us. So we need to work out, okay, well, maybe we can infer what the quality of the good is given the price that we've seen. And so how can we answer this question? Well, the way that a strategic buyer might do this is by sort of running a simulation, not sort of actually running something, but in their head. So how does this work? So the buyer is going to kind of simulate in their head an execution of this whole protocol. So they're going to say that, okay, there's a buyer and a seller. And in this sense, they're going to extend this model with an additional actor called like the world. And the world is going to represent sort of exogenous variables as we've seen before. So the world might sort of choose some quality for the book at the start of this interaction. And then it's going to send it over to the seller. And the seller, once it receives this and receives the title, is then going to sort of locally do some computation to work out how it can maximize its own profit, knowing these values. And then it's going to send over a price over to the buyer. So this is kind of how the price is computed as a function of the quality of the good. So how exactly is that done? Well, this really boils down to how did the seller choose to maximize profit? And this is kind of the cool part, right? Well, how did the seller choose to sort of maximize their profit? Well, the seller would have recursively run a simulation themselves, right? In some sense, the seller is kind of trying to work out what is the highest price that I can sell for this, set for this book that the buyer is going to accept. And this corresponds to running a sort of simulation in its own head, and it's going to sort of simulate a smaller version of the game. And it's going to work out, okay, well, assuming this model of the buyer, who doesn't know the quality, if I set this price, they may accept. And so in this way, we have this, and we can sort of extend this ad infinite. And so this seems like a sort of contrived model. It's actually a sort of idea from cognitive neuroscience. And this corresponds to a theory of mind. And this is actually a good model for how like a lot of humans communicate, etc. And the reason that we chose this kind of formalism is it turns out that there have been recent sort of developments in other PL languages that allow sort of efficiently solving queries over these kinds of recursive probabilistic models. In particular, there's this language called Memo that allows solving this. And so kind of the way that Memo answers queries of this is you can treat these recursive models as a sort of recursive probabilistic program. So in this case, when the world chooses a quality, this can be thought of as sort of sampling from some random distribution. And then this quality is sent over to the seller, and the seller is going to sort of sample from another distribution conditioned on the value of the quality. And then you can sort of, this distribution itself can be another recursive model, but if we kind of cut off the recursion at this point, then we have this model that represents what the buyer is kind of imagining the world to execute. And what the buyer is asking is, what is my expected utility from this interaction? And in other words, this is nothing other than asking a query about sort of computing an expected value of this expression here, which is saying that if the quality is high, then I'm going to get 180, otherwise I'm getting 100. And so the expected utility is just going to be that outcome versus subtracting the price. And so if we can sort of compile this down to sort of a recursive probabilistic program, then languages like Memo allow us to efficiently solve for decision policies. So this is exactly what we do. So we can take our sort of choreographic program expressed as expressed in this language, and then we can do endpoint projection and map these via into Memo programs that represent sort of theory of mind computations from the perspective of each of the participants. And in this process, you can inject in sort of priors about your beliefs about the world, etc., and so forth. And in this process, we can sort of solve for decision policies on how you should actually choose your distribution on when you're making a local choice. And one of the cool things about this is kind of the bias-seller protocol is kind of like the bread and butter of choreographic programming. It's something that I'm sure you've read in lots of papers. And the cool thing about this is we can take this sort of bread and butter program, we can actually recreate kind of rather interesting economic phenomena. So you can kind of get like a market for lemons, where a strategic seller might realize, oh, well, the buyer is going to infer the quality of the good from the price. So, well, I can just jack up the price, and it implies that the good is high quality. And then if you do the recursive computation one step deeper, then the strategic seller might realize that, oh, well, the buyer is going to realize that if I artificially inflate the price, then it's giving a signal that's high quality. So the distributions kind of even out. And I thought this was really fascinating, the way we could kind of recreate an interesting economic phenomenon just on top of choreographic programs. OK, so that's kind of like the high-level overview of this idea. I just want to touch a little bit on sort of directions for future work that I'm interested in looking into. So the first of these is sort of producing a formal semantics for PACT. So what I've presented has kind of a rough implementation in Python. But this is more as a proof of concept. I'd really like to sort of sit down and write down a formal semantics and a formal mapping between these two formalisms, between sort of PACT programs and games specifically, and sort of answering questions about how we can actually map between these and recursive theory of mind models. The second thing is about integration with cryptographic or encryption primitives. So at the start of this talk, I mentioned that a choreography really has no means of enforcing that an agent does a particular local computation. But if we incorporate cryptographic primitives, then we do have means of enforcing that. Maybe we can enforce that the agent sends us a sort of zero-knowledge proof that they did the computation in the right way. And so this maybe opens up the door for PACT being a sort of medium to allow integrating cryptographic primitives into some sort of distributed protocol. And the final direction is, I think, this work has primarily been centered around the bias-seller protocol, because that's pretty ubiquitous in choreographic languages. But I think it would be interesting in a test of this formalism to see whether we could actually take other kinds of game theory examples and encode them within a choreographic language. So things like Vickrey auctions, or English or Dutch auctions, for example, or like cake cutting. Right. So that's kind of like that's the overall that's my high-level idea. So the key takeaways: if we want to sort of scale and enable autonomous interactions between agents, then agents should really agree on their interactions before they run them. They shouldn't be talking in natural language. And if we want formal guarantees, then these should be in a formal language. A choreographic language is presenting at the choreographic workshop. And PACT is kind of the proposal that we've put forward as that language. So thank you for listening. I'd be happy to take any questions.
Thank you very much for the really interesting talk. I'm a little bit curious about this quality that you have there, because the foundation of a lot of economic work for the last 100 years or so has been the subjective theory of value, right? Like, I don't agree with you on what the value of this is, and it seems like you're encoding a objective theory of value inside of PACT. So do you see that as a something to overcome, or do you see that as a modeling choice that's reasonable for some reason? What am I missing there?
Yeah, so thanks for the question. So I would say that, so the question was whether it made sense, whether this interpretation assumes a sort of subjective or objective theory, objective sort of description of value. And in particular, I think actually this is, maybe my explanation was unclear, but I think this is actually a subjective notion of value. Because when you do specifically in the PACT protocol, we don't actually specify what this function is that maps between the quality to the utility that an agent receives, right? This is something that's injected when you do the endpoint projection. So the seller would have to decide, okay, I believe that the buyer values it according to this function, and the buyer would also inject their own beliefs.
Okay, I thought the quality was the utility, so that's where I was getting
Yeah.
confused. Okay.
Can we see the projected code?
I don't have slides on that.
One of my questions was, let me write it down. So kind of what I can do with PACT is sort of, I can analyze a game and see whether it's worth playing in the first place. But have you thought about, I mean, this kind of hinges on the idea that all the participants are actually going to obey the rules of the program that you've specified here. Have you thought at all about kind of a Byzantine setting where I, pretend that I'm Carol and I send a message?
Yeah, so I guess we've kind of elided that discussion in this work. So I know there are sort of like extensions to choreographic programs to incorporate things like faults and failure to deliver messages. So I think that could be extended on top of the core theory. So at least for this work, we're focusing on maybe the core like economic or strategic decision structure. But I think like choreographic languages are a nice formalism for this because this serves as a natural unifying point for integrating like all of these kind of developments that have been coming in from this community into this formalism.
Another question I had was, should I play this game that you've proposed?
So actually, you shouldn't. So I think this is actually recreating a phenomenon of market for lemons, which is that without kind of some impartial adjudicator of the quality of an item, the market kind of collapses. This is like with cars. You end up with like lots of lemon cars where people, the sellers will tell you that it's really good, then it breaks down like after a week.
So is that visible like somewhere here somewhere eventually it gets to the point where like the probability of my getting any benefit as the buyer becomes 0 and then I just decide not to play? Is that visible here, or where did you get that?
So that would come, I think, from solving the game for an equilibria, but that's not part of this. I mean, once you map it to a formalism, then you can solve it for equilibria. But that's not, currently this is just like decision policies.
Got it. Maybe Michael can start setting up. Mm-hmm. And do we have any more questions? Maybe I could ask one more.
So one question I had watching this was, you're not choosing what the local program that gets run is, which is like one of the key things that separates choreographies from like multi-party session types. So I guess the question is, why is choreographies and choreographic programming the right thing here as opposed to something like multi-party session types?
So I guess maybe, I'm not sure. I guess maybe we could talk about offline. I guess choreography, I thought that this was a good formalism. Maybe multi-party session types might be a better.
Yeah, I don't think it's a bad one. I wonder if there's a better one. But maybe not.
Okay, yeah.
It's a great formalism. All right, let's thank the speaker one more time. Have Michael from Northeastern. He's a PhD student, I think a third year, right?
First.
First year. Oh, first year PhD student. Okay. Who's going to be talking about choreographic programming for consensus? Go ahead.
All right, great. Thanks for coming to my talk. And I'm going to be talking about stream choreographies for consensus. This is some in-progress work I've been doing with my advisor, Josh Gancher, at Northeastern. So before I start, I'm going to just quickly talk about consensus. Consensus is kind of a mechanism for getting a cluster of machines to all agree on a linear ordering of events, and all doing that without some kind of single point of failure, like a centralized database. So this is, if you've ever heard like Paxos, Raft, there's also many other variants that do like Byzantine fault tolerance. These are the kinds of algorithms that I'm talking about. And these algorithms are notoriously hard to get correct, which is why there's been a lot of work trying to basically formalize them and reason about their correctness. And so in this work, we're kind of thinking about if there's better kind of programming paradigms to be able to even talk about these in the first place. And choreographic programming is obviously kind of a prime candidate. But as they exist today, there's a lot of challenges for writing consensus algorithms using choreographic programming. So the first is that in many formalizations, choreographies are kind of sequential. So you execute a program, everybody kind of communicates, and then you're done. But servers have to kind of run on forever. So the first thing you might think is, let's just put this into a harness, and then the harness runs a loop. And there's a lot of there's been a lot of work that's already been doing that. The second difficulty is that you need to kind of handle state in concurrent requests. So you can't just run a single loop. The loop has to be able to talk about some kind of persistent state. So if you're thinking about something like a web server, the web server might put the state into a database. And then the database will then kind of furnish your state. But if you're writing the database, as many consensus algorithms are kind of like the core of a distributed database, you don't actually get that luxury. So on top of that, another problem is that a lot of these requests are actually part of sub-protocols. So like in Raft, a node might be simultaneously conducting a leader election, which itself is an entire protocol, while also servicing clients. So you really need kind of a high degree of concurrency. And the final challenge is that there are some patterns in distributed systems that just really hard to express when you have kind of deadlock freedom by construction. So in this work, we're going to explore basically trying to create a new choreographic language, which first of all is able to express a high degree of concurrency. And to follow up on that, we don't want to rely heavily on having a harness that kind of provides the state for us. And so to do this, we're going to use an abstraction called streams. And the next goal is that we want to be able to represent these common system, distributed systems patterns. So this includes things like quorum and leader election and so on. And for this, we'll use an abstraction called clusters. And finally, we would like to be able to do kind of meta theory with this, like being able to talk about equational reasoning and EPP correctness. So yeah, all of this is going to be done kind of using a core calculus. So there's been a lot of kind of prior work on this. If you were here a couple years ago, there's for stream semantics, there's a project called Hydro, which kind of did a lot of this, kind of made a lot of progress in this direction. So we took a little bit of a different approach when it comes to the stream semantics by having a more dynamic communication graph, that's communication topology that's more integrated into the language, so we can kind of talk about the meta theory of the entire language rather than just the communication. And for location polymorphism, there's also been a lot of work in here, but we kind of took a simpler approach, mainly just to make it easier to do meta theory. There's no reason we couldn't extend this our language to incorporate some of these ideas, and we would be really open to doing that in the future. So for the rest of the talk, we're going to kind of go through the main mechanics, and then we'll look at some examples. Right, so first, streams. First of all, there's a lot of different ways streams are kind of formalized, so I'm just going to introduce the way we did it from the start. So I'm going to be using this kind of diagram for our streams. This is kind of like a sender side, and then that side is the receiver. So the receiver essentially gets a source of values. And these values can come from a network, or they could just be kind of produced from like just nothing because you're writing a program. Values can arrive basically any point in time, and they're going left to right. So the 1 is received first in this case, the 2, and then the 3. So this is just kind of the visual language that I'm going to be using for the rest of the talk. And then our streams are also possibly finite. So if you send an end token, then the receiver knows that the stream has ended, and in certain cases, they can kind of go on to the next thing. But it might also not have an end, so it could be possibly infinite for the case of these kind of long-running servers. And of course, we love types, so all of our streams are typed with the values that you send over there. OK, so just to kind of cover our bases, we have a bunch of stream combinators that you can use. A lot of these will be very familiar to you. So when I go over these, I'm going to be showing both kind of like the formal version and also the diagram version. So for empty, we have basically, you can always create an empty stream of any type. And streams are completely local. So we have @L there to kind of show this. We have pure. So pure just kind of returns the exact same element. And it's suggestively named because this is basically the list monad. So we have bind as well. And bind, essentially, you take a stream of values. For every value, you map that to another stream. And then you just take the results and you concatenate them. And this is why end is important, because you need to kind of know when the next stream starts. One important thing here is that bind is lazy. So whenever you receive a value on any of those intermediate streams, that gets immediately kind of pushed out. And so you only react to elements that are received. And this is important because, like, for example, when we go on to write some of our more higher level combinators, like map and filter, for example, will only supply a value to the downstream once you find any element that actually satisfies the predicate, rather than just, like the empty does not produce any value to the downstream. And this is important for our concurrency case, because this means that you can write filters and notify when some kind of event is occurred, but you don't always have to have that. OK. And then the last two I'm going to introduce are also pretty straightforward. So we have scan. This is just list scan. This is important for having state. So in this case, S is a state value that for every single next item is being kind of updated. And in our formalization, we have the stream outputting S as well, just because it makes it easier for for us. And then interleave is going to be this non-deterministic kind of combination of two streams. So you just take whichever value comes first and then combine them into one. So these are our building blocks. These are all pretty much like local operations, as you can see. And with the exception of F, so the Fs in the functions over these are kind of global functions, but we have a type system that restricts. We use the type system to do knowledge of choice kind of restriction, rather than having kind of a runtime thing to kind of propagate it. And this is mostly because a lot of the examples that we're looking at don't actually need to have this kind of branching. We would actually rather make it less kind of expressive here. But we are open to kind of like revisiting this and extending this in the case of like multiply locate values. All right, so let's talk about the stream lifecycle. So this is basically we have a receiver side and sorry, this is kind of like the source side, and that's the receiver side. So in this case, we are introducing something called sync. This, if you are familiar with Rust, like async Rust, the name kind of comes from there, but we're doing it a little bit differently. So the sync is kind of where values come in, and then every value that's received on the sync kind of goes to the stream. And the reason why we have these separated is because these can actually occur on different locations. And so when Alice and Bob are communicating, Alice has this sync that she can use to kind of like basically plug in values, and then Bob will then receive them. And so whenever you create a sync, you create it with a corresponding stream using a rule that looks like this. And we have this uncoordinated. You're not sending an extra kind of value. You're not sending extra messages to do this. And our type system basically enforces that you can't send things in an unprojectable way. And then the final thing is forward. So forward is kind of the thing that actually sets everything in motion. All of the stream combinators I was talking about, those are actually just building kind of inert values. You're just talking about like building kind of functions, and they're just inert values. And then the forward is the one thing in the entire language that allows you to spawn a subprocess that actually starts listening to it. And so this is, because they start consuming streams, these are actually resources, and we have a substructural type system to enforce that you can't reuse sinks and streams after they're consumed. And so this kind of gives us a way to talk about communication over between different hosts. And the type system kind of is important here, and the fact that they're just values before they're forwarded is pretty important, because we have a pattern. This enables some kind of pattern called higher order sinks. And so the question is, what happens when you send a sink over a sink, right? So because sinks are just values, you can send them just as you would any other value. So let's run through this scenario here. You have Alice creates a local channel where you have stream and sink pair between herself. You just take that sink and you send it over to Bob over this existing communication channel. And then when Bob receives it, it's just a local sink that he can do with it whatever he wants, as if it was something that he created to begin with. And even though it's on a different location, they are actually still linked. We're going to have, when Bob sends any values, Alice is going to receive it. So Bob can just plug in any stream. It could be a local value, it could be a pure, or he can hook up a stream that's coming from another location. So it could be something that's networked. And so our local semantics basically is designed so that when Bob receives the sink, he's actually doing a little bit of bookkeeping to save where it came from so that we can figure out how to send it back to Alice. This gives us kind of a way of gives us a way of talking about composable protocols, because you keep the communication kind of internal. And we're going to see an example of how this works. So here's a part of Paxos that I kind of carved out. You have a proposer sending some things to acceptors, and then the acceptors will, based on like some internal computation, send a result back. Normally, when you do this, the responses are all stateless. So when you get the response, you have to then do a lookup and say, oh, did I send this ballot before? Then I have to add an ID to kind of identify which requests I sent. With our approach, you essentially kind of send the sinks over, and then each of the acceptors are basically doing local kind of forwarding while these are still attached. And the important thing here is that the proposers then are no longer having to wonder where, which request it corresponded with. You already had the stream, and it was like exactly corresponding to the request that they were sending. And so one important consequence is that in one of our distant goals is to use this formalism to do verification and talk about maybe sending proof witnesses over the network that get erased at runtime. This makes it a lot easier rather than having to keep kind of like a global invariance on where these requests came from and then having to match them up. So that's streams. That was kind of the bulk of the language. Then we have clusters. These are mostly here to allow us to talk about communication between a lot of different nodes. And so in our formalization of clusters, we kind of allow, we have every single node is doing the same computation within a cluster. And we basically extend the language in order with these global types in order to do this. So the way these are basically abstractions. You can create abstractions, you can apply them, and these are their formers. The important thing is how they interact with streams. So we'll take a look at this. First of all, if you're in a distributed systems context, you always want to do some kind of fan-out operator. So basically, we have a construct called fan-out, which just takes any stream, local stream, and turns it into one stream for every location in a cluster. And the important thing is that these are all local operations. So you're actually kind of doing this duplication locally because, as you remember, forward is the only thing that can actually initiate communication. And so you would chain this with a forward if you wanted to actually do a send. And so fan in is the exact opposite thing. We have pretty much analogous operation, and it's also local. Okay, so I know that was a lot, so let's look at an example of how this works. And so I talked about quorum being kind of a difficult thing to express traditionally. Let's see how it looks in our language. So we're going to have this scenario where you have a list of machines in a cluster, and they're all trying to vote on some outcome. And so in a quorum, you want to take the majority, and then you want to kind of disregard the rest of it. Once you have the majority, you don't care. You can move on. So I'm going to represent this visually and also with our program. You don't have to read the code. It's going to be a little bit dense, but this is just kind of showing how it's built from the primitives that we used. So first of all, we need to get all of these votes into the same machine. So we're going to create these channels to send them all into the same machine so that all of these are located at the same place. So we're going to do the forward on each of those locations, and then we're going to fan them in so that you got one stream with all of the votes. And then from this, from here, you basically have a list of values. So it's just a matter of doing kind of list scan and then doing a filter. And I've left the scan function out, but it's basically if it's true, you add one to the true vote. If it's false, you add one to the false vote. And then the filter only furnishes value if the quorum is actually achieved. So what that means is that the downstream consumer of this quorum just needs to supply the input cluster and then gets back a stream where once you receive any value on it, that means quorum is kind of satisfied. And so we kind of use this to write our Paxos implementation. This is our DSL and lean so far. There's a lot of code because, I mean, right now we don't have kind of a rich inference. So the important thing to note here is that we have a type signature for Paxos that is pretty much as concise as you can get it. You have proposers. This is single decree Paxos, and we can kind of chain this and use this externally too. But we have proposers, acceptors. These are two clusters that you pass in. And then for every proposer, you kind of have values that you want to propose. And then the output is also a set of values, but those values have been decided. And so the program that we've written kind of maintains Paxos' safety condition that that only one value is ever decided. And then notably, all of the communication between these clusters are kind of internal to the language. So you don't have to have any kind of external state or harness that manages this. So finally, I want to wrap this up a little bit by talking about the meta theory, what kind of properties that we're going to investigate. First of all, we're going to look at type safety. So type safety, obviously, we have a kind of a type system. It needs to ensure a lot of properties, so we're doing things like progress and preservation. And then also, we want to study EPP correctness. And this essentially requires us to have like a strong local runtime to do all of this. The next thing is we don't actually forbid deadlocks in this code. So what we've kind of noticed is that traditionally deadlock freedom has served multiple purposes. One is that it kind of ensures programs don't get stuck, and then also simultaneously ensures that you don't have deadlocks. And we found that this was a little bit constraining for some of the patterns that we wanted to express. So we wanted to keep the good parts of being able to ensure programs don't get stuck, communication all gets matched up, and there's no like sends that don't go to the correct places. But we also want to allow kind of like being able to drop requests that you don't care about anymore, like in the case of quorum. And so because we have a stream semantics that is concurrent, we don't actually suffer from the we don't suffer as much when you have things that are just waiting on nothing forever. Okay, so finally, our current progress is we have basically all of these done. For the local language, we're still kind of finalizing the semantics a little bit. And of course, we have our example. And all of this is implemented in Lean as a DSL. So the next steps for us are we're just going to do pretty much the local semantics and the EPP. And I put these in the future work, but really these have kind of been driving the way we've been designing the global language. So it's not like we haven't thought about that at all. And then so as I've kind of hinted at, the distant future for this is we like to use this as a foundation for doing program verification on these distributed systems, because like part of the big problem is that you can't really verify that the Paxos that you've written is correct. So we would like to be able to talk about in the type system ways of saying, oh, Paxos does have this guarantee. And that's all I have. Thank you.
Thanks for the talk, Michael. I'm really excited to see more work in this direction. So during the sort of flow era that you mentioned, one of the things we found was most important for us to reason about when talking about correctness was whether or not the order of streams was particularly deterministic, especially when you start combining streams from different sources. And I'm not sure what your overall ordering semantics there are.
Yeah, so we have been doing a little bit of thinking. Right now we're, so I think the problematic case for us with regards to that would be like doing a scan over like an interleave. We have kind of considered doing something similar to what Hydro did, where we have like some kind of unordered stream versus ordered stream, but so far we haven't really kind of made decisions there yet.
Well, I'm happy to talk about it anytime.
Hi, thanks for the talk. May kind of stole my first question, but I'll ask my second one instead. Oh shoot, what was my second question? It might come to me in a moment.
Sure. I just had a clarifying question around the terminology of sync. When I think of signal flow analysis, I'm thinking sinks and sources and sinks.
Yeah.
And it looks like you have a sink that is like sending messages. So I find that kind of confusing or problematic. And it seems that your use of the word sync looks like a named first class channel that you can pass the channel in a process calculus kind of way. I don't know if clarifying is all.
Yeah, the name really comes from, like, initially when I was thinking about this, I was thinking in terms of kind of Rust's async. I'm not married to the name, so we could, if you have a better name suggestion, we could kind of kind of. Yeah, we can talk about it.
I love naming things.
So so one of the nice things about choreographies is you know exactly how many messages each party is going to receive along a particular protocol, at least within a particular branch of computation, right? So, and when you have this abstraction of streams, you kind of lose that, right? Because you might have somebody who sounds like you can send like a sync over, and you can just send some arbitrary number of messages.
Yeah.
The question is, do you have any way to, for example, say I have a stream, this will receive exactly one event, or at most one event? And if not, do you have any thoughts on how you might support that in the future?
Yeah, that's also a direction we've been thinking about. We haven't needed it for our current example, so we've been not really kind of added that to the type system yet. But I can imagine we would have like 0, 1, or infinite kind of type system, but like stream length kind of thing, and then all the operators would have some kind of interaction with that, but that's all still kind of under investigation. Our primary kind of goal is to be able to just see if we need any of these conditions for our EPP, and if we do, we might expose them into our surface type system.
Okay, maybe last question. So I love this work. I think it's so important to be able to express consensus in choreographic programming. But the one thing that I had to do to get published in the first place was say, like, well, we give you deadlock freedom by design. We give you that. And you've lost that. So what are we going to do to convince people that this work is useful if we don't have that, thing to advertise?
Yeah, I think deadlock freedom is kind of an important thing that we can consider, but the way we would like to kind of consider that in relation to this work is to be able to have kind of like a separate analysis for that instead of making that part of the language, because that then reduces expressivity about what you can write.
I have an answer for that one, which is something that was inspired by something Andrew said, which is we want a better definition of deadlock freedom that lets us still write the programs we want to write. Better meaning weaker, but we can use it better instead.
Sounds like sounds like a great conversation to. Oh. Yeah. We can take this conversation into lunch. Let's thank the speaker one more time.
Thank you.
Thanks everybody for coming.
is going to begin. We're going to start with Miko Bates telling us about, well, several things, but probabilistic choreographies.
Because I would characterize this very much as application focused. But we're talking about AsInst, a language system model for asynchronous instructions so that we can do probabilistic performance modeling of choreographies. So we're starting here with the assumption that we have a choreography. In this case, Alice is going to take some input. She's going to send it to Bob and Bill. Bob's going to do some local computation on it. Maybe he's validating it, forwards that on to Bill. Bill computes the final output. We want to know, how long is this going to take? And of course, anytime you're asking how long something's going to take, that's going to depend on what it is you're actually doing. But it's also entirely possible that what it is you're doing is going to depend on how long earlier pieces of it take to run. So we have this sort of bidirectional feedback. Also, non-determinism is a very natural thing to end up with in concurrent systems, but it's not really sufficient modeling for what we're trying to do. We want to know what the likely runtime is, so we need a probability distribution over all those non-deterministic executions. I'll say up front, we're going to omit recursion. We're also going to omit functions. You could think of this as a compilation target or as a modeling framework. So whatever your source program is, hopefully it doesn't have unbounded recursion, because you're going to need to flatten it out into a list of instructions. OK, so we're building the AsInst instruction system. What do we need to support? We know we want to do local computations. We're not real picky about how those are written. So you're going to be doing some computation, and hopefully it is pure in the sense of not dependent on extraneous things that you can't model. But that's kind of all we care about with that. And we wanted to be able to do communication. So a value that's available at one party, at one location, one participant, will become available to somebody else later if it actually succeeds. It's not guaranteed to succeed, or maybe it is. Maybe you're using TLS. Like, there are lots of different communication models you might be concerned with. And ideally, we don't really want to make this choice for you. Are you doing point-to-point? Are you going to do multicast somehow? Maybe you just have shared memory across your processes, and they can read values each other wrote. We'd like for you to be able to model any of these. So what AsInst provides you is a single instruction form, and you get to decide what it does. X is going to be bound to the result of S of Y's. As the user, you would have to specify what does S do. S is just a name. You're going to write the function body. So it needs a static cardinality and arity, and it needs a coherent type signature. And then that type signature is going to define what it actually does. So you'll have tuples. So if your input is int, what you're actually going to get is maybe a tuple, integer, and timestamp, but also maybe this diamond value, which is null, which is to say it never became available. And so you'll take your arguments, and what you'll produce is not an output or an output with a timestamp. It is a probability distribution, a joint probability distribution across values and timestamps, and also the special null value. So what we've defined so far is data flow programming. This original choreography I showed at the beginning has a really simple data flow diagram where the dependency graph is a nice directed acyclic graph. And guaranteeing that property doesn't actually require much in terms of a type system. You just make sure everything's declared in the right order and has coherent data types. And then when you add your probabilistic function bodies to that, what you get is literally a Bayes net. It's higher dimensional, so it's not just on events, but on actual values, and actually the tuples of values, because the timestamps are baked into each node. But it is still a Bayes net. And that's great, because Bayesian networks are a well-studied phenomenon. Or phenomenon's the wrong word. That's OK. I said we're not going to do recursion, but let's do conditional so that we have something interesting going on. Modeling a conditional in a Bayes net is not fun to do. You have to add an edge from your guard to everything that happens inside all of your branches. Of course, we're interested in the timestamps of things, and we would like to accurately reflect the idea that the branches you don't take never happens. So if your guard evaluates to false or never, then that should force the output distribution of everything in the branch not taken to be the singleton distribution over null. And we have to consider what if the guard is null. And also kind of perpendicular to conditionals, but a lot of times we do things concurrently or in parallel. We don't always want to do everything in parallel. Sometimes one thing has to happen after another. So we want sequencing, the ability to say, don't do that until this other thing has finished. Our solution for that is our guard operation doesn't actually guard on values. It guards on the timestamp. So all of our instructions still only have one form. We say guarded on or gated on G. X is going to sample from S of Y's. And what that says is once or if G becomes available, then you can do whatever S says to get your X value. And if you don't want to gate on anything, that's fine. Just gate on 0, which we special case as always being available at timestamp 0. In order to do a traditional if-else clause, you need this translation. So we define two effects for you, gate true or gate false, that convert that Boolean into something that either becomes available when the thing it's looking at becomes available as true, or if it's false or it never becomes available, then it never becomes available. Gate false does the opposite. And so we can translate this very simple conditional into that completely flat list of instructions over there, where first you take your original scrutiny X, you make the gate the two gates from it, gated on those two, you bind your temporary variables Y in the true branch, Y in the false branch, and then you use first to combine those. First takes whichever one becomes available first, and because we wrote it this way, we know that only one of those, or at most one of those, will ever become available, so we don't have to worry that we're throwing out data there. And this gives us conditionals in a choreographic language. Specifically, we targeted a subset of ozone to do translation and modeling of. It works out okay. So in a conditional, we have in ozone, you have somebody, an owner of the branch guard, and they're going to deal with the conditionals exactly the way I just showed. Other parties, so I say here select and merge, and we haven't really talked exactly about how that works today yet. In a select and merge language, one party owns the conditional and is going to propagate knowledge of which branch they're in on a need-to-know basis out to other participants. So if you're coming into a conditional blind, well, we're going to assume that in your source choreography, everything was copacetic. The source choreography was well-formed, was projectable, and that means it was mergeable, which means that if you're coming into a choreography blind, it doesn't actually matter which branch you go down, just pick one. And by pick one, what I mean here is gate one of them on 0, or whatever you were gating on stuff on before, and gate the other one on never. And then when you get to a select, do bind that to a variable. Usually you wouldn't, but you're going to want to bind that to a variable. And the continuation from there will be gated on that selection variable that you received. This is not as tidy as I'm making it sound. There's annoying edge cases to make sure that the variables you want to use later in the choreography are actually named what you thought they were named and available when you thought they were available. We can put together some kind of pathological edge cases. And I think you can even write choreographies in ozone that do not have a directed acyclic graph representation, which is interesting and surprising. Can we do the same thing for conclaves and multiply located values? It would be nice if we could. Unfortunately, multiply located values, so far, we haven't been able to get play nicely get to play nicely with failable communication. And in asynchronous instructions, it's not just that communication might fail, we care about when messages arrive. And there are very few, if any, situations where you would assume that all of the recipients of a multicast get it at the same time. So if this is what you want, that's future work. So we have the asynchronous instruction system. Hopefully I can answer more questions about it. But first questions are, okay, does it actually work? And how well does it work? And how interested in this should we actually be? So does it work? Yes, it does work. The Bayesian network interpretation that I've described is kind of analogous to the central semantics of a conventional choreographic programming language. We have a distributed analog in which instead of one big Bayesian network that takes place outside of time, we model every variable as a future promise, and those don't start running until their guard is available. And at each discrete time step, they look at the arguments that are available so far and probabilistically decide whether or not to resolve. And we prove that those two systems give you the same results, which is great because nobody wants to use the future-based semantics and nobody has to use the future-based semantics. The caveat there being that you have to make sure that when you're defining the effects used in your program, they are realizable in the time step semantics. Even if you don't actually write out the realization, if you allow an unrealizable effect in your program, then you're going to get time travel. And I am assuming that you don't want that. But continuing on the idea that this works, we did implement some toy examples of it, so we could validate that we got reasonable results. I apologize for not customizing this graph for these slides, but the red lines at bottom show the concurrent execution made available under Ozone of an example choreography that can scale across the number of requests that are happening. The blue lines show that same choreography in the sequential semantics of Coral, and the green are the as-inst models of those two systems. So in the case of Ozone, it correctly identifies that it's going to be much faster. In the case of Coral, it nicely tracks the best case scenario, but there are some sources of latency that we failed to model, and so the actual likely evaluation is much worse than what as-inst predicted. So that gets into how well does this work? And the answer is, first of all, you have to have good models of your individual effects. The as-inst system doesn't help you write those. It doesn't help you determine that they actually model the things you're doing. But if they are good, as-inst will let you compose them and get a good model of the whole thing. The thing that as-inst actually gives you is a Bayesian network representation of the joint probability distribution of the entire program and every variable inside of it, which could be quite large. The good news is, or let's start with the bad news. The bad news is that Bayesian networks are not magic. The scaling with the number of variables is still expected to be exponentially difficult to compute on as the number of variables goes up. The good news is that that's a worst case, and Bayesian networks are nicely studied, and there are lots of special cases where you can do a lot better than that, and also a lot of practical cases where it looks bad, but when you actually run it, it turns out okay. Is this big, important work? Well, it's not that big an improvement on the status quo. A lot of the techniques I've described are not novel. So the Bayesian network I've described is a special case of a system described as a temporal node Bayesian network, where the nodes are annotated with timestamps. The distributed semantics, if you squint at it, is kind of doing the same thing as a dynamic Bayesian network, which has been studied for even longer than a temporal node Bayesian network. So I actually think the most interesting result here is that we're able to do this result on choreographies by just adapting off-the-shelf systems. That was the original promise of choreographic programming, was you can write your distributed system in a single program and do conventional static analysis on it and get results that apply to the real distributed system. So I think that's cool. that this is just an incremental improvement. But we also didn't do this just to advance the state of the art. We actually wanted this for a bigger project. Specifically at University of Vermont, we're on the topspin team for a DARPA program. I promise you that PWN2 is pronounced doubly pwned. So we're studying weird networks, which is just the word for a communication medium, the use of which is difficult or impossible to detect by outside parties. And some of the early challenge problems are of the form, how long does it take to actually send something over one of these networks using all the cryptographic tools that it's built out of, which can involve retries, failable communication, a lot of random wait times between messages. And that is a pain in the butt to model, and that's what we built this for. So what does DARPA want this for? Well, stated purpose is to help people living under totalitarian regimes communicate amongst each other or with the outside world. Other obvious use cases would be to help American agents, I guess, in those same locations exfiltrate data, or to prevent, monitor against people in American data centers exfiltrating data. Last year when I presented at PLDI, it felt like kind of a non sequitur at the end of my presentation to remind the audience to fight fascism in our daily lives. And then on the plane ride back from Korea, America bombed Iran. So I, fingers crossed, have better ways of making the world a better place in my daily life than worrying about whether or not the work I've done here is going to have good or bad effects in the world. But we should be thinking about it. I forgot to start my timer. Oh. But here's the full preprint, which goes into all of the gory details. This is a practically oriented system that we intended to solve a problem and not necessarily to be mathematically elegant. So if you'd like to read it and ask me questions, or ask me questions without reading it, those are both great courses of action.
Your timing was perfect. We have about 5 minutes for questions.
I just have a clarifying question about
Yep.
the end of it. You said you were building this for a project. Was it then a smaller part of a bigger project, or did this give you the solution you wanted for some part of the weird network problem?
So this gives us, the specific thing that this gives the team is validation that their choreographic-ish system is actually going to model the way the real system behaves, which is like a lot of the time you would just say, well, we have this thing and here's our model and they look about right. And this lets us give a more formal proof, that the analysis is sound and will match what you observe in the wild.
I find this project really exciting as a guy working on the Coral programming language, and we just made an IDE plugin for Coral. One of the things we're looking at is interesting static analyses that we can run, and I think it would be really awesome to write a choreographic program and have an analysis that shows a little indicator at the very top of the choreography that says, well, the minimum time we expect is this, the average time we expect is this, and that's hugely important in the context of, like, for example, cloud computing or something like that. So I'm wondering how feasible would that type of analysis be to do in a production programming language like Coral? And also, you talked about performance. How long did it take to get that analysis?
So your second question first. I don't know. I worked on this with a team of people at Vermont. I should go up to the very beginning so we can see who they all are. It was Stephen and Ernest who did the physical implementation, and they'd be able to tell you how long it took. I know that when they start working on the actual challenge problems for doubly pwned, some of those run for hours or days. So building it into your IDE doesn't sound like the thing you're going to end up doing, is my guess. So you would need a mechanical translation from Coral into as-inst, and that would require a formal solution to those variable name problems that I mentioned when you're translating your conditionals. I think that can be done, but that is not something we have off the shelf at the moment. Right now it's by hand.
I'm thinking back to Kieran's talk from this morning.
Mm-hmm.
Could we do game theory with Bayes nets? How hard would it be to talk about that instead of performance?
I don't know. That said, is time the only thing we can talk about here? One way that I was thinking about this at different times was having two planes. So there's the data plane and the time plane, and they can talk to each other. But like, you'll notice when I said these values have types, the type is just integer, and then the value is integer and timestamp. Could we add other metadata besides just time to it? What I found is that time behaves a special way, and everything else kind of just behaves like data. So yeah, you could put other metadata in there. It's going to behave more like data than like time, which is possibly a good thing.
Okay, we have time for maybe one more question while the next speaker gets set up. I have a question. You have the ability to have messages fail. What network assumptions are you actually relying on?
So you can write your own effects and decide what assumptions you want to make. We don't make any assumptions. If you want to have the assumption that one party can just read off of somebody else's hard drive magically, go ahead. If you want to assume that it's just UDP or something like that, then all you really need is a probabilistic model of how long or how likely it is for a message to get across. I guess the two load-bearing assumptions are don't do time travel, and more dubious, don't let effects affect each other. And like, that might not be realistic if you have limited bandwidth.
All right, let's thank Miko again. All right, up next we have Ashton Wiersdorf. Is that pronounced correctly? Okay. Ashton Wiersdorf, who's going to tell us a bit about event-based choreographic programming.
Okay, I did push the button and maybe that's what I did. Okay. We doing good? Okay, all right. Yay, thank you AV people. Yay. All right. Okay, well, very happy to be here. I am going to talk to you today a little bit about my library, CoreX. I wanted to add the THX like sound for that, but didn't figure out how to do that. Also, by way of names, so this is a library for the Elixir programming language, hence the EX. A lot of Elixir libraries have EX. I just love all the puns we have in choreographic programming. I thought unicorn was just peak. So, you know, here in choreographic programming, we have this beautiful model of going from a this high-level overview and splitting it out into pieces. And my library brings choreographic programming to the very pragmatic world of Elixir and production concurrent functional programming environments. To start off, it is truth universally acknowledged that a computer scientist in possession of a good theory must be in want of an implementation. I think Jane Austen said that, something like that. CoreX is a very, I don't know if very is the right word, but it's much more of a pragmatic focused system. And I've already made a version of CoreX. I'm going to talk to you a little bit more about like new directions I'm taking CoreX. To do this, I went around and looked at a bunch of different distributed systems. So Elixir libraries mostly, but a few other systems as well. And what I really wanted to do was to see what can't I do in CoreX or some other choreographic programming language. I found a few compelling applications, and so then I thought, what would I how would I want to program these systems? And what would I need in a choreography to do that? So I wrote some fantasy programs and eventually found some core building blocks that would help me express all the patterns that I wanted to. So in quick order, the building blocks were I wanted event handlers. If something happens unexpected in the system, I want some other part of the system to be able to respond to that. Another one is some way to control who's participating in a system. Systems create and destroy processes all the time. And finally, to make these two things happen, I realized I would need first-class process references. I'll get more into what that looks like. Now, to set expectations, I've kind of got this path up to event-driven choreographies. I'm not quite there yet, but hiding in the bushes, we found this lovely thing called first-class process references. So that's what, so we've got first-class process references working in a lot of ways. It's awesome, and I'm still working on implementing the rest of it, but I'm optimistic. So without further ado, let's talk about one of the most compelling use cases I found for something that I'd like to write with a choreography. So I'm going to build a web server. This design is borrowed from a web server library for Elixir called Thousand Island. The way Thousand Island works is like this. You have your server, and you have a listener process that's listening on the operating system port. When somebody comes in and tries to make a connection, that process goes, oh, got a new connection, and it grabs a process from this pool of acceptor processes. These are all just waiting. And that acceptor then does the TCP handshake. So now you on your server, you've got a socket, which is great. And then you take that socket and you wrap it in a process to manage its lifetime. So now we have, that's why it changed from dotted to a full thing. Now you have a process managing the life cycle of this socket. You can send this process a message and it will forward it back over the TCP connection, whatever. So now you've got a process client, and then the acceptor spawns another process meant to manage the life cycle of the web application itself. And these talk back and forth to each other with request, response, request, response. And ideally, we'd like to kind of partition this off into its own little choreography. Once this is done, the acceptor moves back into the pool and is ready to keep working. This is nice, both because it can accept requests very, very quickly, but also if something, say, happens to the client, like the client shuts down unexpectedly and crashes, then the app worker can cleanly clean up whatever resources are left over. And vice versa. If the app crashes, then the client could notice that, send a nice 500 error message back to the client, and then shut itself down gracefully. So there are a few aspects of this that are tricky. First, you need to be able to spawn new processes. You need to involve new processes in choreographies, and you need to be able to respond to events. So here's the choreography I wrote. Now this is aspirational. That said, I said this slide is taken almost verbatim from my dissertation proposal. I say almost because I've updated this choreography, and it's a lot closer to what we're actually able to implement. So I'm pretty optimistic that most, if not all of this, will make it into the final version. So choreographies and stuff are kind of grow up a little bit. I don't know. You start off with these role definitions that talk about the kind of actors in your system, and they each you might need some of these actors to know about other actors. For example, the client should know about its app worker, and the worker should know about its corresponding client. This becomes important when we get to events. Here's the choreography for the main listen loop. You've got the listener process. L is the listener process. It's got the OS socket that listens to. It grabs an acceptor process off of its pool, round robin style, and holds on to that until somebody comes knocking on the door. It's the LCON. And then it starts up a little sub-choreography. So there's actually a sub-choreography right here where it says, hey, acceptor, take the connection, go. And then it goes just back, recurses back, and keeps listening for new connections to come in. This is where the acceptor creates a client and worker. I've deleted the bit where it does the TCP handshake, but the idea is it does a TCP handshake, hands that off to the client worker, and then the app can start running. And so then the app is pretty basic. Oh, this is the setup application. In this place, the client monitors the worker. So if the app shuts down, then the client process can send a 500 back to the web browser or whatever waiting on the other end. And then here's the application loop. It's pretty simple, even though it's a little bit longer, but this model is like a stateful application. And then finally, here are the events. This top one models if the client gets a message that its app worker has gone down, then it can send a 500 error back. And then the client, if the client shuts down suddenly, then it can clean up. This is probably the part that needs to change the most. So if anybody has any inspiration on what should go here, I would love to talk to you after. So to recap, some of the new things in this are, first you have first-class actor references. I've got some expression in the choreography language that next acceptor references another actor. I also make new processes in addition to pulling them off of lists and whatnot. And then we've got these event handlers. So those are the new things in CoreX v2. I'd like to talk to you a little bit about how we actually do macro expansion. Projection. We use macro expansion to do projection. And that, so Elixir's got a fabulous macro system. It's AST-based. Its macros are hygienic, and they're procedural-based macros. And what this gives us is a lovely language-integrated choreographic programming system. So it kind of sits at this little, this funny in-between space. It is a library. You install it like a library. All the syntax highlighting works like it's embedded DSL. You get all of the IDE features and whatnot. But in addition, the macro expansion phase acts as like a compiler step. And so we can do analysis on it. So you get wonderful error messages in the terms of the language that the IDE can understand, even though it's your embedded domain-specific language. So it's pretty neat. Now, onto Elixir's process model. So Elixir is based off of it runs on the Erlang virtual machine. And so it has really lightweight processes. Each process has a mailbox, and processes can also monitor each other. So if one process goes down, then another message can be notified of that. This is fabulous. Now there's a special flavor of process called a gen server. And a gen server is just a library to realize a common pattern with processes. It's basically a process that can have some state and take action in response to messages that come in. And this turns out to be a great model for actors. Here's an example of how a gen server might look. You describe a module. So here's a module to like make a counter where you can say like, hey, increment, increment, increment. Okay, give me the count and reset yourself back to 0. So yeah, you say use gen server. Says I'd like to make a gen server, please. They all have some initialization steps. So this is just setting up like the start count. And then there are different ways that you can send messages to the gen server. This one would be like, if I get a message that is the atom inker, then I add 1 to my state. And it does a functional update, so like there's no mutation under the hood. But nice and clean. It gives you a nice stateful process. And here's another one where if you, this is when you get the message get and reset, send back your state, your counter back to whoever called you, and then your new state should be 0. So that's all with that. There's a tricky bit here, and that is with gen servers, you don't want to stick an explicit receive inside of a handler, because that might break things with how the gen server would work. So we had to find a way, and this is using CoreX v1 notation here. We had to find a way to make these receives work. So anytime you do a receive in CoreX, it actually has to get split across 2 message handlers. So for example, here's the first half of the choreography where Bob says something and sends it to Alice. But then, and that's the top function there. But as soon as Bob wants to receive the price from Alice, he has to have a separate handler for that. And these two get kind of tied together with a just some kind of UUID, some identifier to tie them together. And all this gets bundled up in the gen server state, and there's a little bit of a runtime that manages this. Please see our first paper for more details on this. Anyway, but the point is this is really complicated. And it makes projection really tricky. So why would you want to bother with gen servers at all? Well, for starters, gen servers are very easy to monitor. And the second thing is that they can do out-of-order message handling. The gen server runtime handle will, when it gets a message from another actor, it puts it inside of its own mailbox so that if the messages arrive out of order, it can reorder them or handle them in the order that it's expecting to. We use sieves, kind of like Ozone, to make sure that messages come as expected. And finally, these gen servers can actually participate in multiple sessions at the same time. The way the gen server state works is that they have a network, which is just like what other processes they know about. They have this inbox, again, that you can reorder. They keep track of what module is implementing all of the local code of the actor. And then they also keep track of all the sessions that they know about. So this is just a map of a bunch of sessions, and each session holds the local variables at that point, as well as a separate stack. And so this is kind of like it's like a gen server, but it's got multiple versions of itself that it can teleport between. And each of these are keyed with something called an SRAID. Yeah, they're all keyed with that. The SRAID stands for session ID, role ID, and actor ID. So the session ID is generated when you instantiate a new choreography. That's the session. The role ID is like, am I a worker? Am I a client? Am I a database handler? Am I a bookseller? Whatever. And the actor ID is a unique token for the choreography. I'll get into that in just a minute, what that is, after I talk to you about some new problems that I found. Because I was like, I would love to write this choreography, and then all these new problems started snowballing. The first one is we need something like a role checker. Not like a type checker, but it's a role checker. Because the role Alice is up here, but down here in the choreography where I'm trying to talk about a process that implements Alice, there's no Alice right there. The actor names aren't where we need them anymore to do projection. So we use this signature right here and perform something kind of like a type check to propagate that A refers to a process named Alice. Now, I would have said that Elixir does not have types, and so like we don't get this for free. Elixir 1.20 dropped last week, I think, and so now we have types in Elixir. So, but still doing something like this is a little bit like there's still no user annotations, so there's still a ways to go with that. But I am curious to see like what I can do with Elixir's new type checker. But anyway, there's also some more stuff here that I'll get to in like 3 slides. Anyway, so we have a custom role checker. We also sometimes need explicit role casts. So like here, this could be synthesizing a new process identifier. And there shouldn't be anything wrong with that, but the problem is the role checker doesn't know what role we're talking about now. So if you do need to know what it is, you can annotate it like that. And the double colon is an infix operator in Elixir, so the Mackers are happy. So role checker. The second challenging issue was what if a role shows up more than once in a choreography, like this? Imagine you've got 2 worker processes, and they need to switch the jobs that they're working on for whatever reason. So you've got worker 1. It's here, and then you've got worker 2, and that's where it's at. They're both called worker. Remember how I talked about the SRAID, and it was session ID, role ID, and actor ID. So these get unique actor numbers, and so when it projects, the projections have, there's some more of the rest of the SRAID is right here, but then there are 2 copies of this function inside of the projected module. And so this one will handle the actor ID 1, and this one will handle it when it's the actor ID 2. And so it will dispatch between them. And the neat thing is this works even in like really turgid situations where here we've got 3 workers, worker 1, 2, 3. Worker 1 sends 2 to worker 2. Worker 1 sends 3 to worker 3. Workers 2 and 3 both send messages back to worker 1, and then worker 1 combines them. So we should expect 2, 3 at the end. Fun thing is, I have gotten this working whether or not you instantiate it with 3 separate processes or 1 process in each of the 3 roles. It keeps the variables and stacks separate. So, yeah, path torture, yes. Oh, I don't think I propagated that up here, but yes, path torture. So that was a fun headache to resolve. And then one tricky issue, and there's some relation to knowledge of choice with this. If I create a new process up here at the top and then call run job on it, how does that process know where to find the other processes? I'm calling it right here. How does it know to find the other processes? How does it know that's even involved in a choreography? It's just floating in the void until somebody talks to it. The answer I came up with is when you do a function call, that's when you can wake up a referenced process. This is very important in the example that we showed earlier where we have a client and a worker that just get like produced out of the void, ex nihilo, and now you're like, okay, now go and start off this choreography. But now there's a question of who notifies the actors. Now we could have like some central process to do this notification and help introduce all the processes to each other. There's some prior art that does something like this with durable processes. But I want to try to avoid that. So the limitation I came up with was all processes going into a function have to be either all top level or there has to be one hub. All top level means that you're working with variables that are just like variables by themselves, and presumably they should already know about each other. When you kick off a choreography, there's one process that's going to do that, and so it's going to introduce everybody. So if you're just working with a subset of those processes, they should already know how to find each other. No issues there, at least so far. The one hub is here. I'm trying to call a function with A. B is not involved here. Oh, I forgot to mention this. This first argument to the choreography is the set of process identifiers that you want to instantiate the choreography with. Sorry, I meant to put that earlier in the talk. But so A is a process. X and Y are also processes, but B knows their process identifiers. A does not. So that means B is the hub in the situation, and so the projection for B will contain all the code to introduce and wake up X and Y and let A know what their PIDs are. So that should work. Here's where we run into trouble, where we have processes that don't have a common hub. I thought that we might do something automatic with this, but it turns out it'll just be easier to, and it's better to give the programmer control of who is the hub, how do the process identifiers get there, etc. So those are the 3 headaches that I've kind of overcome. And more challenges remain. For example, what is the right model for events? Should we just allow arbitrary interrupts? I'm still not sure about that. Can we find other ways to wake up actors? And maybe you guys have seen something that I have missed that will come and bite me. But anyway, so happy to talk about these. Thank you very much.
We have a few minutes for questions.
One basic question to start. Why would you want to have 3, why do they all have the same name in that picture? Why don't you call them worker 1, worker 2, worker 3?
That would then be 3 different roles.
Why do you want them to share the role, same role?
So we've got a bunch of, in this instance, we have a bunch of processes that have this, that we want to be interchangeable with each other. Right.
So they all function as the accept
they all function as the acceptor, right? Maybe you have a pool of workers and you want them to have like a uniform interface, but then maybe one of them decides like, hey, you know, I don't have a GPU, but that worker, I know that worker's got a GPU. Let's switch roles, but they've got the same API to the system. And so, I don't know. Also, why not?
It's like a sub-role sort of thing. Like we're all workers, but in the context of run, this is worker one, this is worker two.
Yeah. That is kind of implicit, though, with the actor IDs, as these get under the hood a 1, 2, 3. So, yeah. Is there like a sub-role? That's an interesting idea, though, having like subtyping for actors. Okay.
All right. Maybe one last question while the next speaker gets set up? Or you have a question and on the next speaker?
So can you elaborate on why you need the no common hub rule? Because A, B, and C are all present and know that we're going to go into the choreography compute. So why can't they all just wake up their children?
They might have more than just those children. They could, but how are they going to communicate? They can wake up their children. That's not an issue. But then, how are their children going to be introduced? Whose house is going to host the play date? Good question.
Right. Let's take Ashton again.
Thank you.
News is that now we get to go on to some very pure theory. The bad news is that we haven't done the hard work here. The rest of my life interrupted. I'm now working with a company called Obsidian Systems, doing some cryptocurrency engineering and other work in Haskell. But I still think this is a really cool line of research, and hopefully it has a future. Now is a great time to thank the other names up here. So Mark Pastroni has been working in Denmark on choreographic programming, I believe, for over a decade now. Joseph Neer has been my advisor through 6 years of grad school. Sheun Quinn taught me Lean and fixed a bunch of my Lean code. It's unfortunate none of them made it here today. So 2 years ago, I claimed that select and merge choreographic programming languages can do all the same stuff as conclave and multiply located value programming languages, and vice versa. We still don't have an actual proof for that, and one of the reasons is because it's not a very well-defined claim. So what's a select and merge language? What are conclaves and multiply located values? And what actually is the nature of the equivalence we're trying to claim here? So finally, late in the afternoon today, we can define some of these terms. So when we say select, select is an in-your-language communication operator distinguished from the normal COM communication by the fact that its argument is always a static literal. And then merge is not an operation inside your language. It's a meta operator. It happens during the endpoint projection compiler pass or whatever. And its job is to merge the branches of a choreography, of a conditional, which you don't know which one you're going to take. And so merge will say, okay, well, if you do the same thing in both of them, just do that thing. If you're receiving a select in one of them, then that turns into then you'd better be receiving a select in the other one, and that's going to turn into a lookup table of offer and choose syntax, which comes from multi-party session types, or I guess session types more generally, perhaps. And then critically, if you're not in one of those two situations I just described, merge will fail. Merge is a partial function and will identify, hopefully statically, some ill-formed choreographies that cannot be projected. So Fabrizio Montisi wrote a textbook on choreographic programming, and the textbook CP language is procedural choreographies. It works exactly as I just described. He was also involved in the Core Lambda project, which was a functional choreographic programming language. And one of the follow-ups to that line of work showed that you can do a thing in Core Lambda called distributed choice types, where there are multiple owners involved in a tuple. And the behavior you get out of that is very much like, in fact, basically the same as a multiply located value. It's been my observation that once you have those, if you have select and you have something that acts like multiply located values, I don't think you need a communication operator. I think you can do that as syntactic sugar based on select. So this kind of sketches out a Punnett square. These are all select and merge languages, but some of them are limited to singly located values, and some of them have multiply located values. Some of them, although to be clear, I don't believe anyone has actually implemented this bottom row. This is a thing that I believe exists, but take my word for it. So we have communication as syntactic sugar. Can you do that same trick without multiply located values and get a usable complete language? I don't actually know. I think so, but I'm not going to claim that you can. And what's the difference between them in this direction? So when you have multi-located values in a select and merge language, the thing that lets you do is recycle knowledge of choice across sequential conditionals. So we go into one conditional, and the owner of that branch propagates knowledge of choice using selection to the participants. If you have multiply located values, then you can leave your conditional, do a bunch of stuff in the surrounding choreography, and then branch again without doing more knowledge of choice specific communication. But is that just purely ergonomic? Because the way you're supposed to use select and merge languages is that intervening stuff can just be duplicated across your branches, and they only have the one conditional branch that spans the whole choreography. So maybe that is a purely ergonomic difference. Let's do the same kind of exercise for conclaves and multiply located values. So a conclave is a in-language operator, won't always be called conclave, that lets you use a choreography with one census, with one set of participants, in a place in your program where you would expect a choreography with some larger set of participants, a larger census. A lot of languages that I've seen do have this, and it's implicit in the act of calling a subroutine or calling a function, and that's actually a really easy and reasonable way to do it. Multiply located values are more of a type abstraction, or you can bake them into your central semantics. The sort of pretense there, the abstraction, is that you can have one value which is known to multiple parties, and so in your program or in your semantics, maybe you don't want to copy that value across them all. We just say there's one value and everybody knows it. That's a multiply located value. What I've demonstrated in previous work is that these two things can be used as a knowledge of choice strategy without select. So that was my paper in which I described multi-core and a couple other implementations with Lindsay and several other people last year. Previously, Clore is a closure implementation which has a lot of the same capabilities, but it works a little bit differently. So they don't do broadcasts natively, they just do point-to-point communication, but they let the program update the types. So the set of people who own a multiply located value can change over the course of the program. The communication operator adds people to the list of owners, and in that context, your multicast is just a syntactic sugar for doing a list of sends. So that fills in two of the squares. You absolutely can do a conclaves and multiply located values language with both multicast and flow-sensitive mutable typing. Does that get you anything that you would need or that you don't have in the other systems? I don't think so. And then in the lower left quadrant, is there a useful language, a useful way of interpreting a conclaves and multiply located values system that doesn't have mutable types and also doesn't have multicast? I don't think there is, but I haven't ruled it out. So that covers kind of the big paradigms, the two phylum I've been describing. Phylum, phyla, phylas, I don't know. But that's not comprehensive. Like, choreographic programming is getting to be a large and diverse field of study. So selection types are cool. You see those in Coral. First-person choreographies are pretty new and probably somehow related to multi-tier programming. If you start removing capabilities from conclaves and multiply located values, you get the version 1 of Chorus, which was presented a couple years ago. And if you keep deleting stuff, you get Hascore. In my dissertation last year, I showed that the original multi-core API doesn't take full advantage of everything Haskell has to offer. And you can actually do everything in multi-core without any built-in notion of a located value at all. All you need is the conclaves. And I don't think that that is specific to Haskell. I think that that relies on the notion of choreographies as data. So we know programs are data. But if your choreography is data, then a multiply located value is just a special case of a choreography. And then predicate transformers is up on top because although I don't think anybody's like using those implementations, their knowledge of choice strategy probably is dominant in the sense of subsuming everything else. Probably. So let's go back to the idea of what does it mean to translate? What's our equivalence relationship that we're after? Bisimulation would be great. So if you can do a step there, you can do a step in the equivalent translation. But I don't think it's promising. So if your conditional operation is something that you do semantic steps to evaluate, then in select and merge, first the owner branches, and then they send knowledge of choice related communication to everybody else. In conclaves and multiply located values, you do your knowledge of choice communication first, and then you branch. Yes, so confluence is your next choice. We can show that the two translations are going to end up in the same place, which, yeah, I think that's probably pretty straightforward, but it's also not really what we care about. In choreographies, the communication is kind of what we care about. The final evaluation in most systems is an afterthought. And even if it was just you want the output value, the intermediate communication has security implications, has performance implications. So confluence is not really the thing that we want. And also, once you support recursion, it's not going to be that much easier anyway. What I think we can show is some sort of eventual agreement on the intermediate values. And it's going to take a sec to explain what that means. So the first thing we want is all of your communication and also all of your local computation should be binding variables, because the variable states, the assignments to the variables are the thing that we're going to track. Normally, select in most languages doesn't bind a variable, but it's data over the wire, so we got to track it, so it needs to bind a variable. Since we're doing recursion, and also maybe you just want mutable state, so you can write to variables more than once, that's fine. And however, if you're writing to the variables more than once, then if I see x equals 5, I shouldn't have to worry about whether that was a message you received or something you computed locally, because those have very different implications. And whether you sent something over the wire is one of the things we're trying to show equivalence about. So we add to our type system both the owner and the originator of all data, and that way we can lock in if x is a message received from Bob at Alice, then everywhere x gets assigned, it's that message. It's going over that channel. Variables are kind of like channels. On the other hand, we don't, I'm skipping to the last bullet here actually, we don't necessarily need to support multiply located values in the semantics. Our type systems can do that and guarantee that they'll check out, but at the semantic level, it's fine, just copy the values across parties. So that gives us kind of, when we think about our variable store, the state at any given point of the program of all the variables, you can think of it as having two dimensions now. There's the name of the variable and what party it's at. But then we're going to add a third dimension, because our semantics, when you do a write to a variable, you're not just going to overwrite its value, you're going to append to the list of all values it has taken on. So the ongoing behavior of the program will only ever look at the head of that list, but What you get out of your whole evaluation is the trace of every value that every variable was assigned to. And this is kind of what that looks like. I haven't shown here the actual choreography that is taking steps. I've shown the variable store. So there's 5 variables owned by 3 different participants. And there are 3 possible steps that I've said this choreography can take from here. So P is ready to evaluate Z for the first time. And so we can do that. Q is ready to evaluate Y for the second time. And so we can write 5 in there. R is ready to evaluate W for the second time, so we could step that way. The thing that should stand out about this is that when Q stepped and wrote 5, we put 5 in for Y as well, even though P is not, sorry, we put 5 in for P dot Y as well. But P is not ready to evaluate Y for the second time. So we don't actually have, and the reason why I say that we can do that is because I'm talking about the central semantics where we paper over some of those differences. And in order to get agreement with our network semantics or distributed semantics, we need to say, okay, like what actually is the relationship between the two? It's not one-to-one. It's this more subtle kind of coverage, eventual coverage. If you can bind a variable in one of your semantics, then there's going to be a corresponding binding that can happen in the other, and vice versa. What's this going to let us do? We want to define representatives of all the paradigms I tried to lay out in some sort of schematic earlier, so that we can show translations from one to the other and correspondences of the possible variable stores that can result out of their computation. And then if those correspondences are at all well behaved, we can start showing transitive either dominance or equivalence classes amongst them. I think mostly equivalence classes. And then we can talk about what is our strategy for doing that. The strategy that I'm proposing is to define one big language that does as much of it as possible. So we have one syntax, one concept of endpoint projection, one semantics, and some degree of type checking that supports communication, multicast, multiple located values, select and merge, and hopefully, or I should say, maybe some other bells and whistles. I think we can put predicate transformers in there as well. And then the concept would be, when I say representatives of the paradigms I showed earlier, we have sub-languages, a static analysis, a static check that you can do on one of these programs to say, ah, yes, this fits in the conclaves and MLV's paradigm, and whatever it can step to semantically, that satisfaction will be preserved. So it's a member of this sub-language. And then our translations say, okay, given something that passes that static check, we can translate into something that passes this other static check, and the space of variable stores that you get out of executing either of them is going to be the same. We haven't done that. So, how am I on time?
You're doing, let's see here. You have about 10 minutes, including questions.
Okay, well, I'm done.
Well, we have plenty of time for questions. So, questions?
So in the eCoop paper about Core Lambda, there is a way to, like a very loose sketch of how to express a distributed agreement type in a language that only has, sorry, not an agreement type, it's a multiply located value type.
Yep.
In a language that only has select and merge. But it was just a sketch. So one thing that's unclear to me at this point, is that actually sufficient to fully express all the expressivity that you want in out of multiply located values? Is that already a sufficient translation, or is there stuff that you can do that we can't do?
It probably depends on what it is that you want your language to do. So Core Lambda is a lambda calculus. It has a kind of algebraic data types in the sense that it's got unit, it's got tuples, it's got choices. And if that's all you want, then I do not see any reason why you can't do whatever you'll be doing with multiple located values in that system. Actually performing the translation, nobody's written it out. It's not as easy as it first looks because you need to, so the way you represent a multiply located unit is by a tuple of units. The way you represent a multiply located choice is by a choice of tuples. And so how the structures get lifted is not, well, nobody's shown it exactly yet. Well, yes, I think it's possible for that case. If the data type you want to represent is a function or a choreography, you might need something more powerful. You might need something baked in. But in the case of choral, I think you probably have more options because you can represent these more complex data structures.
More questions?
Hey, thanks for the talk. So on your first slide, you asked, what do we mean by translated? Like, what's translate? And maybe to phrase that question differently, to phrase the question in terms of the equals sign, we could ask, what does equals mean? And so I guess, what do we mean by equivalence, right? Like, one question is, do we care about like the same externally observable behavior, right? And you kind of got into that a little bit when you said, well, no, we also care about the intermediate results and the side effects and so on. But another thing we might care about is efficiency, like communication efficiency. So, and it seems like they wouldn't be equivalent in that regard, but maybe you could comment on that.
Absolutely. So my assumption has been that if you are communicating the same amount of data between the same pairs of parties in the same order, there shouldn't be differences in efficiency. Now, right off the bat, that relies on the assumption that all of your performance bottlenecks are in your communication, which might not be true. And also, like, maybe it's wrong. Like, I think it's true. So my assumption has been that we can represent all of the communication as a trace, as part of our variable store trace, and that kind of covers what we want. And since the communication is included, and also the order should be included, because that has security implications, so that should cover our performance concept. But like, there's other concepts of performance.
So I have a question. So this idea of looking at the possible traces that the choreography can produce, and including like what communications it does, is something that I've thought a little bit about with some students, work that ended up transforming into something completely different. So,
as it goes.
But we were looking at it in the context of proving deadlock freedom, and so I'm wondering if you've thought at all about that in this work.
So I've been assuming that you want deadlock freedom, and
like, have you thought about using the traces to actually define what deadlock freedom is, or anything like that in any?
So I guess there's kind of two different things that I've defined and sketched out and begun building. One of which is sort of the computational model of here are some traces. And we probably could define deadlock freedom in terms of that. However, I've been thinking about it more in terms of the actual language that operates within that computational structure and being able to define deadlock freedom in the usual sense of, if this thing is projectable and if your language, if any program in your language passes whatever minimal type system the language has, and also is projectable, then it will have preservation and progress and correctness of endpoint projection, and those together give you deadlock freedom. Could you define that in terms of the underlying computational model? I haven't tried.
Any other questions? All right, Dan?
One thing I was confused about when you were dismissing the concept of by simulation, you said that that the order in which you do evaluate the guard of a conditional is reversed. In one case, you send and then you evaluate, and in another case, you evaluate the condition and then you send.
Yes.
But I mean, that seems like too fine a level of granularity. I don't care when we're evaluate. Like, I consider that like a tau transition, and therefore it doesn't matter if you do it either way. What I care about is the sequence of communications that I'm observing. So couldn't you do like a weak by simulation instead of a strong one?
Yes, well, maybe. I think if your weak by simulation is like you do big steps up till communication and then you are all set, you do weak steps up to communication, and the communication is the thing that needs to match up. I don't know, because like in a conclaves and MLV's language, the communication that enables knowledge of choice at the time of branching could have happened arbitrarily early in the program. And in a select and merge program, the communication that allows knowledge of choice can actually happen, like a lot can happen between you branch and then somebody needs to know which branch they're in. In fact, they can participate in the branches as much as you like before they actually learn which branch they're in. Yeah. So, like, no, I'm not going to claim it's impossible. I'm going to claim it looked hard and I didn't do it.
All right, let's thank Mako again, and can the next speaker come up and sit up?
Good? Okay. Yeah. So not my student, not my postdoc, senior faculty, and he was asked in a bunch of places that, are you a student of Ankush? And he was not happy about that. All right. So yeah, today I will be talking about parametric choreographies, specifically describing this language paracore. And these are basically choreographies over party sets. And I will explain what that means. Okay, so just a little bit of motivation. As we know, many protocols out there, specifically distributed protocols, have parametric number of parties. And when I say parametric, I don't mean dynamic. I mean something like two-phase commit or MapReduce, any of these protocols where the number of parties don't evolve during the protocol execution, but they may be deployed with different number of parties at the start. So you may want to deploy a protocol with n participants, like 5 participants, and then with 10 participants, and so on and so forth. But during the protocol execution, they don't evolve. And so there are many examples of this, like two-phase commit, which has 1 coordinator, p participants, MapReduce, which has 1 coordinator, and mappers are reducers, and so on and so forth. Okay, And so many traditional choreographic languages generally support a constant number of parties, although there has been a lot of recent work on supporting more than that. So our effort is in that way of supporting more than just a constant number of parties. And the goal of the language is that to deploy the protocol on different number of parties, I should not have to re-implement the program. I should write the choreography once and then deploy it on different parties without rewriting anything. Okay, and so I will first give you a very, very high level description of what are the main features of the language, and then I will show you some examples and then some theory. Okay, so we have the standard expressions like P.E, which is a local expression at a party. P.E communicated with Q.X, meaning the party P communicates the value of expression E to a party Q, which binds it to variable X. We have conditional branching, and we have synchronization labels like L and R to communicate whoever did the branch to other parties which branch it to. And we have only two new constructs into the language, which is one is a for loop over party sets. So here I have a for P in capital P, which here capital P is a set of parties, and P is a party variable that iterates over that set of parties. And then C1 is the body of the loop. And so you're basically executing choreography C1 for all the parties in capital P. And then C2 is the loop continuation, so the choreography that executes after the loop is finished. And then we have an associative array communication. I'll explain what this means a little bit later, but the high-level idea is that when you're collecting values from a parametric number of parties, you generally want to store that in an array, which is indexed with the same parties that you are collecting the values from. Okay, and so before I go to an example, I wanted to just highlight a little bit more about the language. As I showed you already, we have party variables like P. These party sets, capital P, they are pairwise disjoint. So you can have many party sets in the program, but they are all pairwise disjoint. And this gives us this property of no self-communication, and which also gives us deadlock freedom. I already talked a little bit about associative arrays. And then one point that I will come back to later, but we have a projection algorithm that's linear time, and there are no runtime checks in the projected program. Okay, so this is an example of the two-phase commit protocol in our language. But before I go through the choreography itself, I just want to give a high-level description of the protocol. So in this protocol, there is one coordinator and participants. And collectively, they want to decide to either commit a transaction or abort a transaction. And so this happens in two phases, hence the name two-phase commit. In the first phase, the coordinator sends a prepare message to all the participants. And the participants individually decide whether they want to commit or abort. And then based on that, they compute a vote, and they send it back to the coordinator. So the vote will be either yes or no, depending on whether the participant wants to commit or abort. Then the coordinator collects all these votes, and then it counts the votes. And if every participant votes yes, then the coordinator decides to commit. Otherwise, it decides to abort. If the coordinator decides to commit, then it sends this L message to all the participants. And if it decides to abort, then it sends the R message. And then after receiving this L or R message, the participants will either commit or abort. Okay, so now I will go through this step by step for this program. So starting with a for loop over all participants. So participants here is a party set. And this P represents for one abstract party in that set. And so you are sending this prepare message to each participant. And because you don't really, in this example, I don't care about the data. Usually there is some transaction data associated with the prepare message. But because I don't care about it, I just used an underscore that it just receives a message and just ignores it. Okay. So that's the first loop. One interesting aspect that I want to highlight is that the semantics of our language are designed in a way that this for loop treats this participant set basically as an unordered set. So the semantics is non-deterministic in choosing the order in which you iterate over these participants. So we don't have to fix an order. And the language is designed that way. The projection, all of that handles for this kind of non-determinism. OK, so that's the first loop. This is where the prepare message is sent to all the participants. Then you want to collect the votes from the participants. So internally, what each participant would do is call the prepare function. And usually, this is the transaction information that it gets from the prepare message. But again, I ignored that. And so it calls this prepare function locally. Each participant does that, computes the vote. And then the vote is sent back to the coordinator. And the coordinator is storing that in this associative array called votes, which is indexed by the same party P, that is the sender of the vote. And again, the reason we need an array is because if I just used a regular variable here, then it would repeatedly get overwritten as you're executing different iterations of the loop. And we don't want to do that. We want to actually collect all these values. And so we use an array for that. And this is actually enforced by our type system that whenever you have a parametric party, like P, sending to a different party, it must always send to an associative array, which is indexed by the same party P, which is the sender. So that's enforced by our type system. OK, so that ends the first phase. Now the coordinator has to make a decision. So it will take this votes array, call this count votes function, which will just count the number of yes and no votes. And based on that, the coordinator makes a decision whether it wants to commit or not. And this naturally acts as a barrier between the first and the second phase. As you can see, that the first phase has to fully finish before the second phase starts, because the coordinator has like a data dependency here. It has to complete this decision, for which it has to wait for all the votes to come in. And therefore, our semantics ensures, even though it can do out of order execution, that the first phase must fully finish before the second phase starts. OK. Say that again? No, we don't need a construct to specify a barrier. Maybe in some situations you may need to, but here it is tracked directly by the semantics. Because this line depends on votes being calculated, and votes is being received here. And the coordinator is involved in the communication that comes later. So the coordinator cannot do this, or any of the participants cannot do this until this decision is computed. It's an aggregation operation, yeah. OK. So that's the first phase. In the second phase, now you again iterate over all the participants. And based on the decision of the coordinator, you either send the L message if the coordinator decides to commit, and you send the R message if the coordinator decides to abort. And accordingly, in the then branch P, every participant P commits. And in the else branch, every participant aborts. And again, why do we need these synchronization labels? Because the behavior of the participant depends on whether it receives or whether what decision the coordinator makes. And therefore, the coordinator needs to send its decision to all the participants. OK. And so before I talk more about the theory of our language, I wanted to quickly come back to this point that you want to implement the program once, but you want to deploy it with different number of participants. And to show that, I wanted to show how the pipeline of our language works. So there are three phases. One is where the programmer writes the choreography. This is where type checking also happens. And at this stage, you assume that party sets are fully abstract. You have no idea what parties belong in each set. The only thing you know is that party sets are mutually disjoint from each other. Beyond that, you have no other information. Yeah. They can be empty, yes. I don't think in any of our examples we used empty sets, but they can be empty. There is nothing preventing that. Yeah. Actually, I will. That's a good point. I will come to a semantic rule in 5 slides that will answer that question, which I just realized. Okay. So yeah, in the first phase, you are writing and type checking the choreography. And then in the second phase, this is where you are instantiating the party sets. So this is basically like saying that, okay, this participant set contains these specific parties. This is given as an input to the endpoint projection algorithm. So the endpoint projection algorithm takes the choreography, takes this instantiation, and then generates the control programs. Yeah. What do you mean I treat everything uniformly? No, the coordinator gets a different, like every party in a party set gets the same code, but there can be many different sets, and a party in a set, like in different sets, can get different code. You can even think of the coordinator as a singleton set. Yeah. Okay. So then you are instantiating, and the reason we are instantiating the party sets here, we can even show that we maybe don't even need to do it here, is that the control programs that are now generated, they're fully executable, because everything that was abstract, namely the party sets, have been fully concretized. So at this point, there is no non-determinism, no unknowns. Everything is fully determined. And so these are executable, and then we deploy these programs, and then you can execute them. And this is the another point to see here, is that if you want to deploy the same choreography with different party sets, then you just have to change phase 2. You don't have to rewrite the choreography. Okay. So now coming to the endpoint projection. So here I will talk about the choreography's first projection on the coordinator, and then I will show the projection on the participants. And the main thing to note here is that a for loop generally would project to a for loop for any parties that are outside the set that it is being iterated on, but will translate to or project to one iteration for any parties that are inside the set. And so because the coordinator is not in this participant set, this for loop will translate into a for loop for the coordinator. So it will just say send prepare to all the participants. Then in the next for loop, here this is local computation at the participant, so the coordinator doesn't care about that. The only thing it does is that it receives votes indexed by P from the party P. Then you compute the decision based on calling the count votes function on the votes associative array. And then again, you have another for loop where based on the decision, you either send the L message to P or the R message to P. And then there is some return, which you can ignore the return. Choreographies don't need to return, but here we are requiring them to. So that's the projection on a coordinator. And then comes the projection on a participant, which as you can see is much smaller. And that is because it doesn't have any loops. All the loops go away because each participant is essentially executing just one iteration of the loop. And so this for loop just translates to receive a single message from the coordinator. This for loop translates to 2 instructions. First, compute the vote, and then send the vote to the coordinator. And there are no actions here for the participant. And again, this translates to another a single action, which is you receive either the L message or the R message. If you receive the L message, then you call commit. Otherwise, you call abort. Okay, so that's the example. And yeah, I have time. Okay. So in the last 5 minutes, I will talk a little bit about the meta theory of the language, starting with the semantics. So traditionally, maybe not traditionally because there are both kinds, but our language is functional, and but we use this environment-based semantics. So instead of just saying C1 steps to C2, I have this environment which stores mappings of this form, p.x maps to v, saying that at party p, variable x has value v. And this is a bit technical, why we need that. So I will ignore it, but if you have questions, I'm happy to answer. So it contains mappings of this form. And this judgment is stating that choreography C1 with environment sigma 1 steps to choreography C2 with environment sigma 2. And R and B are, R is the readx label. And this is something we use when we are proving operational correspondence. And B is a blocked set which tracks which parties can take a step, which parties are blocked. This is like both of these are standard for choreographic languages. Okay, so there are lots and lots of rules. I think there's at least 5 or 6 pages of rules in the language, and I will not explain all of those. I will just focus on some of the rules that relate to the for loop. The rest of the rules are pretty standard. And so the first rule is what to do when you have a for loop like this. For some xp in this set p, you execute C1 followed by C2. So here is where the non-determinism comes in, where I was saying that you choose any arbitrary order of loops, of a for loop. So here I pick non-deterministically a concrete party C belonging to that set. And then I pull out one iteration of the for loop. And I'm saying this choreography C1 executes under this environment sigma 1. And all that sigma 1 is basically what sigma is, except this variable xp is now mapped to C, because I'm iterating on that particular iteration where xp is C. And then I compose this iteration with the remaining iterations. So p prime here is basically the original set p minus the party C. So it's like not very different from a traditional for loop where you take one iteration out and you compose it with the rest of the iterations. And then you have the base case of this where you will keep doing this. Eventually, this party set P will become empty because you finished all the iterations. And that's covered by this rule where this party set is empty. So this answers your question. What if the party set is empty? We have a rule for that. Thank God. And so if the party set is empty, then you just transition to C2 because you've exhausted all the iterations. This rule may look a little bit complicated, but it's not really. This is stepping one iteration of the for loop. So I'm saying if sigma 1 C1 steps to sigma 1 prime C1 prime, then this whole choreography steps to, instead of having sigma 1 C1, now I have sigma 1 prime C1 prime. And I also update this global store sigma prime. I'm not going to go into details on why we need to do that, but it is to prove soundness. And so you keep stepping this internal iteration. Eventually, it steps to end, meaning that the iteration is over. And at that point, you get rid of this iteration, and you go back to executing the remaining iterations of the for loop. OK. So a couple of theorems about the language. We have the standard theorems of progress and preservation. I didn't talk at all about the type system because there isn't anything very interesting happening at the type system level. The only interesting thing is that the type system is enforcing that there is no self-communication, and it's using the fact that party sets are disjoint. But this progress theorem is basically saying that if you have a well-typed choreography, then either it's already a value, or there exists a new choreography and a new environment, sigma prime C prime, such that sigma C steps to sigma prime C prime. And then you have a preservation theorem, which is also very standard, saying that if you have a well-typed choreography and it takes a step, then you can ignore all that. But the new choreography that you will get will also be well-typed. And then we have the standard operational correspondence theorems in both directions. Again, this may look complicated, but it's not really. This is basically saying that if the choreography takes a step, a single step, then you project this choreography down to a system, pi. And basically, this theorem is saying that if the choreography can take a step, then the corresponding system can also take a step. And this is where the readx label R comes into play, because the step that the system takes is somehow related to the step that the choreography takes. And this is this relation. So this is the forward direction. Then there's the backward direction, where if the system is taking a step, then and the system is basically a projection of a well-typed choreography, then you can also show that the choreography will take a corresponding step. And with the same things, that the step will be related, and the new choreography will be a projection of, the new system pi prime will be a projection of C prime. Okay, and so we also have implemented this language, or like basically an interpreter for this language. And we tested it on a few different protocols. And here I'm basically showing the number of lines of code of the choreography versus the endpoint projection. And in general, we found that choreographies lead to something between 15 to 60% reduction in the lines of code that you have to write if you were writing a choreography versus writing the endpoint projections directly. And our endpoint projection algorithm is quite fast. Even with 15 parties, the code that is generated in less than 2 milliseconds. And I'm not going to go into other results, but we can show that the generated control programs are also efficient. They scale linearly as you increase the number of participants. Okay, so just to summarize, so what was new? The only thing really that was new was we introduced this for loop with abstract party sets that were unknown during type checking, but were later concretized. And we support out-of-order execution. We have linear time endpoint projection. The theorems, we have deadlock freedom because we have progress and we have operational correspondence. And so, yeah, I already talked about that. And we have an implementation that we tested on a few different protocols. And I had showed you the results. So this is it. Thank you.
We have time for one quick question.
Your meta-theoretic results, they are proven regardless of instantiation of party sets, or they hold for a particular instantiation of a party set?
No, they hold for because when you are doing the semantic step, the semantic step only applies to an instantiation. So when you are really showing progress in preservation, you are doing one instantiation. And you're saying that this is like a runtime choreography. It takes a step, so it's a concrete one. It's an instantiated one.
All right, I'm afraid we are out of time, but let's thank Ankush again. And then in 30 minutes, we have the business meeting. So please come back. We'll talk about running the choreographic programming community. Hope to see you all there.
And if you're not going to that, you can still meet us for dinner at 5:30 at Avanti Food Hall, I think it is. Let me know if you didn't get that and you want to still join.
Thanks very much. Have a good break.